Welcome to this exploration of computer science, designed for learning at your own pace. Whether you're actively listening or letting the information wash over you as you fall asleep, you're surrounded by thinking machines, in your pocket, on your desk, embedded in everything. But how does a device made of sand and metal understand instructions, remember information, make decisions, and connect to billions of other machines across the planet? The answer is more surprising than you might expect. We essentially taught rocks to think. If you find this helpful, consider subscribing for more content on science and technology. And we'd love to know, where are you listening from tonight? Drop your city or country in the comments below. Now, find a comfortable position. Let your body settle. And let's discover how computers actually work. The impossible machine. You're holding a small glass rectangle that contains more computing power than existed on the entire planet in 1960. It can access nearly all human knowledge in seconds. It can show you the face of someone on the other side of the world in real time. It can generate images that have never existed, compose music, translate languages, navigate you through unfamiliar cities, and perform billions of calculations per second. At its core, at the most fundamental level, it's doing exactly one thing: turning electricity on and off. That's it. Every website you've visited, every photo you've taken, every video you've watched, every message you've sent, all of it reduces to patterns of electrical current flowing or not flowing through microscopic switches carved into silicon. This fact should stop you in your tracks. How does flipping switches produce intelligence? How do on-off patterns become memories, decisions, creativity? How does electricity moving through sand create the experience of watching a video, reading a message, playing a game? The answer involves one of humanity's most profound intellectual achievements. We discovered that everything, absolutely everything, can be reduced to patterns. And once you can represent something as a pattern, you can manipulate it, store it, transmit it, transform it. The universe, it turns out, doesn't care whether information exists as ink on paper, electrical charges in silicon, or grooves in vinyl. Information is substrate independent. It can live anywhere. But that realization came slowly, built on centuries of mathematical insight and decades of engineering innovation. And it started with a simple question: can we build a machine that thinks? The dream is ancient. Humans have always been tool makers, and we've always dreamed of tools that could think for us. Ancient Greek myths spoke of Talos, a bronze automaton that defended Crete. Medieval scholars imagined mechanical servants and thinking heads of brass. In the 18th century, mechanical automata entertained European courts, clockwork musicians, chess-playing Turks, and write-in children, though all were ultimately tricks requiring human operators hidden inside. But the question became serious in the 19th century, when mathematics itself began to change. For thousands of years, mathematics had been about numbers and shapes. Then, in the 1800s, mathematicians started asking stranger questions. What is mathematics? What can be proven? What does it mean for something to be computable? A British mathematician named George Boole proposed something radical in 1854. You could do logic with mathematics. Not arithmetic, not geometry, but pure logical reasoning. True and false could be treated as numbers, and or not could be treated as operations. like addition and subtraction. This seems obvious now, but it was revolutionary then. Boole had discovered that thought itself might follow mathematical rules. Then came Charles Babbage, an English polymath who designed, but never completed, what he called the analytical engine in the 1830s. This mechanical device, driven by steam and gears, would have been able to perform any calculation that could be described as a sequence of operations. It had memory, a processing unit, input via punched cards, and output via a printer. It was a computer, conceived entirely in brass and clockwork, a century before electronics made such machines practical. Babbage's collaborator, Ada Lovelace, understood something even Babbage hadn't fully grasped. In her notes on the analytical engine, she wrote that the machine could manipulate not just numbers but any symbols that followed rules. It could, in theory, compose music or create graphics if those could be represented symbolically. Lovelace had seen that computation was more fundamental than arithmetic. She'd glimpsed the universality of computation a century before anyone could build it. But nobody built it. The analytical engine required thousands of precisely machined parts. Victorian engineering couldn't manufacture them reliably enough. Babbage died having completed only fragments. The machine remained a beautiful dream. The breakthrough came from an unexpected direction: pure mathematics, divorced from any thought of building actual machines. In 1900, the mathematician David Hilbert posed 23 problems he believed would shape mathematics in the coming century. The 10th problem asked whether there was an algorithm, a mechanical procedure, that could determine whether any given mathematical statement was provable. This became known as the Entscheidungsproblem, the decision problem. Could there be a universal method for determining mathematical truth? A young British mathematician named Alan Turing tackled this question in 1936. To answer it, he needed to define precisely what mechanical procedure meant. What could a machine actually do? Turing imagined the simplest possible computing device: an infinitely long tape divided into squares, each square either blank or marked with a symbol. A reading head could move left or right along the tape, one square at a time. It could read the symbol on the current square, and, based on that symbol and its own internal state, it could write a new symbol, change its internal state, and move left or right. That's it. That's the entire machine. It sounds absurdly simple, almost childish. A tape, a reading head, some simple rules. No memory beyond the symbols on the tape. No sophistication, no intelligence. But Turing proved something astonishing. This simple machine could compute anything that could be computed. Any calculation, any logical operation, any algorithm, no matter how complex, could be reduced to these simple operations: read, write, move, change state. This is a Turing machine, and it's not a real machine but a thought experiment, a mathematical abstraction. Yet it defined computation itself. If you can describe a procedure precisely enough that a Turing machine could follow it, then it's computable. If you can't, it's not. Turing then proved something disturbing. There is no solution to the Entscheidungsproblem. There is no universal method for determining mathematical truth. Some questions are undecidable, not because we haven't been clever enough to solve them, but because no procedure could possibly solve them. This was a profound limit on what computation could achieve, discovered before computers even existed. But Turing also proved something liberating. There could be a universal Turing machine, a single machine that could simulate any other Turing machine. Give it a description of another machine and its input, and the universal machine could produce the same output. One machine could be any machine. This is the theoretical foundation of every computer you've ever used. Your laptop, your phone, a supercomputer, they're all universal Turing machines. They can run any program, simulate any algorithm, because they're not specialized calculators. They're general-purpose machines, capable of becoming anything software tells them to be. Turing had answered a question about the foundations of mathematics, but he'd also, accidentally, invented computer science. The timing was not coincidental. The same year Turing published his paper on computable numbers, the world was sliding toward war. Abstract mathematics would soon become urgently practical. During World War II, code breaking became a matter of survival. The German military used Enigma machines, electromechanical devices that encrypted messages with seemingly unbreakable complexity. Each day, the settings changed. Each message used different rotor positions, the combinations numbered in the billions. Breaking Enigma required processing vast numbers of possible settings, far more than humans could check manually. The British built machines to help. The bomb, designed by Turing and others, was an electromechanical device that could test potential Enigma settings at high speed. It wasn't a computer in the modern sense. It was a specialized code-breaking machine. But it demonstrated that machines could perform intellectual work previously thought to require human insight. Meanwhile, across the Atlantic, the Americans were building something more general purpose. Artillery tables, used to aim guns accurately, required extensive calculations. Before computers, these were done by hand by teams of human computers, mostly women, who spent hours with mechanical calculators working through ballistics equations. It was slow, tedious, and error-prone. The U.S. Army funded a project at the University of Pennsylvania to build an electronic calculator. The result, completed in 1945, was ENIAC, Electronic Numerical Integrator and Computer. It weighed 30 tons, occupied 800 square feet, and contained 17,468 vacuum tubes. When turned on, it dimmed the lights in the surrounding neighborhood. It generated so much heat that it required industrial cooling fans, but it could perform 5,000 additions per second. This was miraculous. Calculations that took humans days could be done in minutes. Artillery tables that required weeks of work could be computed overnight. ENIAC had a problem, though. It wasn't truly a universal machine. To change what it calculated, you had to physically rewire it, reconnecting cables and resetting switches. Programming ENIAC meant spending hours or days reconfiguring the machine's connections. It could compute anything, in principle, but changing what it computed was agonizingly slow. The solution came from John von Neumann, a Hungarian-American mathematician working as a consultant on ENIAC. Von Neumann had read Turing's paper on computable numbers. He understood the concept of a universal machine, a computer that could become any machine by writing instructions from memory. Von Neumann proposed a revolutionary architecture: store the program in the same memory as the data. Don't hardwire instructions into the machine's physical configuration. Instead, treat instructions as just another form of data, numbers that tell the machine what to do. The machine reads an instruction from memory, executes it, and moves to the next instruction. To change what the computer does, you don't rewire anything. You just load different instructions into memory. This is the stored program concept, and it's how every modern computer works. Programs are data. Instructions are numbers. Memory holds both. The computer doesn't know or care whether a particular memory location contains instructions or information. It's all just numbers, all just patterns of electrical charge. This insight, that programs and data are the same kind of thing, is almost mystical in its implications. It means a program can modify itself. It means one program can create another. It means a computer can run an emulator that simulates a completely different computer. Software becomes infinitely flexible because it's not bound to hardware. The same physical machine can be a word processor, a video player, a web browser, a game console, anything, just by loading different patterns into memory. ENIAC was completed too late to affect the war, but its successors, EDVAC, UNIVAC, and others, established the paradigm. Computers were no longer room-sized curiosities. They were tools, and institutions began buying them. Initially, they were used for scientific calculations, weapons design, census data processing. They were expensive, rare, and required specialized knowledge to operate. The idea that everyone might someday own one seemed absurd. But something was happening in the background, a quiet revolution in materials science. ENIAC used vacuum tubes as switches, the same technology used in radios and early televisions. Vacuum tubes worked, but they were large, fragile, power-hungry, and they burned out frequently. ENIAC required constant maintenance. On average, one tube failed every 2 days. In 1947, researchers at Bell Labs demonstrated a new kind of switch, the transistor. It was solid-state, no vacuum required. It was tiny, about the size of a pencil eraser. It was reliable, with no filament to burn out. It used a fraction of the power, and it could switch on and off millions of times per second. The transistor is arguably the most important invention of the 20th century. It made modern electronics possible, and critically for computers, it made switches cheap, small, and reliable. Early transistors were discrete components, individually manufactured and wired together. But in 1958, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor independently developed the integrated circuit. Multiple transistors fabricated together on a single piece of silicon. This was the birth of the microchip. Now you could pack dozens, then hundreds, then thousands of transistors onto a chip the size of your fingernail. In 1965, Gordon Moore, co-founder of Intel, observed that the number of transistors on a chip seemed to double approximately every 2 years. This became known as Moore's Law, and it's held true for over 50 years. Think about what that means. Doubling every 2 years. That's exponential growth. Start with 2,000 transistors in 1970. By 1990, you have 2 million. By 2010, 2 billion. Modern processors contain tens of billions of transistors, each one a microscopic switch carved into silicon using light and chemistry. And every one of those transistors is doing the same simple thing, switching on or off based on electrical signals. That's it. There's no magic. Each transistor is a valve, allowing current to flow or blocking it. But billions of these simple switches, organized correctly, connected in precise patterns, following carefully designed rules, can simulate anything. This is the impossible made real. We took sand, silicon dioxide, beach sand, purified it, doped it with impurities, carved patterns into it with light, and created thinking machines. We built intelligence from switches. We made rocks compute. But switches alone don't explain computers. You could have all the switches in the world, perfectly reliable, infinitely cheap, and it wouldn't matter if you didn't know how to organize them. The hardware, the physical substrate, is only half the story. The other half is abstraction, the idea that you can build complexity in layers, each layer hiding the details of the one below. You don't need to understand transistors to write a program. You don't need to understand machine code to use a spreadsheet. Each layer of abstraction makes the one below invisible, allowing us to build higher and higher, creating complexity without drowning in details. This is what we'll explore throughout this journey. How we went from switches to algorithms, from electricity to information, from silicon to intelligence. We'll see how each innovation built on previous ones, how theory and practice intertwined, how mathematics and engineering collaborated to create something that seems almost magical, but is, at its foundation, utterly physical. Computers are the most complex machines humans have ever built, yet they're also the simplest, because at the bottom, beneath all the layers of software and abstraction, there's nothing but electricity flowing through switches. Everything else is pattern. Everything else is organization. Everything else is us, imposing structure on chaos, teaching sand to think. To understand how we did it, we need to go back to the beginning, to the moment when someone proved that thinking machines were even possible. We need to meet a man who never built a computer, but who defined what computation itself means. We need to understand the Turing revelation. The Turing revelation. Before anyone built a working computer, before vacuum tubes or transistors or silicon chips, a young mathematician proved that thinking machines were possible. Not just possible, inevitable. And he did it with nothing but logic, pencil, and paper. The year was 1936. Alan Turing was 24 years old, recently graduated from Cambridge, working on abstract problems in mathematical logic that seemed to have nothing to do with building actual machines. He was trying to answer a question posed by the German mathematician David Hilbert. Could there be a mechanical procedure, an algorithm, that could determine whether any mathematical statement was provable? This sounds technical and remote, the kind of question only mathematicians care about. But it touches something fundamental. Is there a foolproof method for finding truth? Can reasoning itself be mechanized? Can thinking be reduced to following rules? To answer this, Turing needed to define what mechanical procedure meant. What could a machine actually do? What were the limits of computation? Nobody had ever asked this precisely before. Machines of the 1930s were either specialized calculators, built for specific arithmetic operations, or mechanical automata following predetermined patterns. The concept of a general-purpose computing machine didn't exist. Babbage had imagined one a century earlier, but his analytical engine was never built, and most people had forgotten about it. Turing approached the question from first principles, Forget about gears and electricity. What is the most basic thing a computing device could do? Strip away everything unnecessary. What's the minimum required for computation? He imagined a device of almost laughable simplicity, an infinitely long tape divided into squares. Each square either blank or marked with a symbol, say a 1 or a 0, though any symbols would work. A reading head that could examine one square at a time. The ability to move left or right along the tape, one square per step. The ability to erase or write symbols. And a set of rules determining what to do based on the current symbol and the machine's internal state. That's the entire machine. No memory except what's written on the tape. No complexity, no sophistication. Just read a symbol, follow a rule, write a symbol, change state, move left or right. Repeat. This became known as a Turing machine, though Turing himself called it an automatic machine or a machine. It's not a real machine. You couldn't build one. The infinite tape makes that impossible. It's a thought experiment, a mathematical abstraction, but it captured something essential about what it means to compute. Turing showed that this absurdly simple machine could perform any calculation that could be described as a precise, step-by-step procedure. Addition, multiplication, finding square roots, solving equations. Anything you could break down into basic operations, a Turing machine could do. The key insight was universality. You could design a Turing machine to add numbers. You could design a different one to multiply. You could design machines for specific tasks. But Turing proved something more profound. There could be a universal Turing machine that could simulate any other Turing machine. Feed the universal machine a description of another machine and that machine's input, and the universal machine would produce the same output as if you'd run the specific machine directly. One machine could be any machine, depending on what you told it to do. This is the theoretical foundation of modern computing. Your laptop is a universal Turing machine. So is your phone. They're not specialized for any particular task. They're general purpose. They can run any program because programs are just descriptions of what to do, and the machine follows those descriptions mechanically. Software doesn't change the hardware. The physical machine remains the same whether you're writing a document, playing a video, or browsing the web. What changes is the pattern of instructions loaded into memory, the description of what operations to perform. The universality Turing proved in 1936 explains why a single device in your pocket can be a camera, a map, a library, a communication device, a game console, and 1,000 other things. But Turing proved something else, something darker and more unsettling. Not all problems are computable. There are questions that no algorithm can answer. Not because we haven't been clever enough to find the algorithm, but because no algorithm could possibly exist. The proof is elegant and disturbing. Turing asked whether there could be an algorithm that determines whether any given Turing machine would halt or run forever. This is called the halting problem. Take any program with any input. Will it eventually finish and produce an output, or will it get stuck in an infinite loop, running forever without stopping? This seems like the kind of thing a sufficiently smart algorithm should be able to determine. After all, we can often tell by inspecting a program whether it will halt. Surely, with enough cleverness, we could develop a general method. Turing proved this is impossible. Assume such an algorithm exists. Call it H. Feed H, a description of any program and its input, and O(H) tells you whether that program halts or runs forever. Now, construct a perverse program, call it P, that does the following. P runs H on itself. If H says P halts, then P deliberately goes into an infinite loop. If H says P runs forever, then P immediately halts. What happens when you run P? If H predicts P halts, then by construction, P doesn't halt. If H predicts P runs forever, then P halts. Either way, H is wrong. The assumption that H exists leads to contradiction. Therefore, no such algorithm can exist. This is not a failure of human ingenuity. It's a fundamental limit on what computation can achieve. Some problems are undecidable, not difficult, not requiring more memory or faster processors, impossible, in principle, for any algorithm. Turing had answered Hilbert's question about mathematical provability. No. There is no mechanical procedure for determining whether statements are provable. Some mathematical truths are beyond the reach of any algorithm. This was a profound result in mathematical logic, closing off a hoped-for path to certain knowledge. But Turing had also, almost accidentally, invented computer science. He'd defined computation precisely. He'd established its limits, and he'd shown that universal machines were possible. Machines that could simulate any other machine simply by being programmed differently. The timing was significant. Turing published his paper on computable numbers in 1936. 3 years later, World War II began. Abstract mathematics suddenly became urgently practical. The German military used Enigma machines to encrypt communications. These were ingenious electromechanical devices with rotating wheels called rotors. Each rotor could be set to one of 26 positions. The machines had 3 or more rotors, plus a plug board that swapped letter pairs. The number of possible settings was astronomical, billions of combinations. Each day, German operators would set their Enigma machines to new configurations according to distributed key sheets. Messages encrypted with one day's settings couldn't be decrypted with another day's settings. Even if you captured an Enigma machine, without knowing the daily settings, you couldn't read the messages. Breaking Enigma required testing vast numbers of possible settings, far more than humans could check manually, even working around the clock. Turing, working at Bletchley Park, Britain's code-breaking center, designed a machine called the bomb to automate the search. It wasn't a computer in the modern sense. It was a specialized device built for one purpose, but it demonstrated that machines could perform logical operations at scales impossible for human calculators. The bomb exploited weaknesses in how Germans used Enigma. Certain messages had predictable content. Weather reports often began with wetter, German for weather. These cribs, known phrases that appeared in encrypted messages, could be used to narrow the search space. The bomb tested settings mechanically, using electrical circuits to check whether potential settings would transform known plain text into the intercepted ciphertext. When it found a match, it stopped, and human operators could verify whether the setting was correct. This wasn't general-purpose computation. The bomb couldn't be reprogrammed to solve different problems, but it showed that machines could augment human intelligence, handling the tedious work of checking millions of possibilities while humans provided insight and judgment. Meanwhile, Turing was thinking about more general machines. He wrote a report in 1945 after the war, describing a design for an electronic computer that could store programs in memory. He called it the Automatic Computing Engine, or ACE. It would use vacuum tubes as switches, mercury delay lines for memory, and, crucially, it would store instructions in the same memory as data. Programs would be numbers, just like any other information the machine processed. This was the stored program concept. And, while Turing wasn't the only person thinking along these lines, John von Neumann independently developed similar ideas. Turing understood its theoretical foundations better than anyone. He'd proven mathematically that universal machines were possible. Now he was trying to build one. ACE was never built as Turing designed it. Politics, funding issues, and institutional resistance slowed the project. A smaller pilot version was completed in 1950, after Turing had left the project. But the ideas lived on. The stored program architecture became the standard. Every modern computer descends from these principles. Turing's insight was that programs and data are the same kind of thing. Both are just numbers, patterns of symbols. The machine doesn't distinguish between instructions that tell it what to do and information it processes. Everything is encoded in memory, and the machine reads from memory, interprets what it finds, and acts accordingly. This seems obvious now. Of course, programs are files on your computer, just like documents or photos. Of course, you can copy a program, modify it, create new ones. But this was revolutionary. Previous machines had fixed functions. To change what they did, you rebuilt them, rewired them physically. With a stored program machine, you just load different numbers into memory. The implications are staggering. Programs can modify themselves. One program can create another. A computer can simulate a completely different computer, running software designed for hardware it doesn't even have. Video game emulators work this way. Modern computers simulating decades-old game consoles, recreating their behavior in software. The universality. Turing proved mathematically became engineering reality. But Turing was thinking even further ahead. In 1950, he published a paper titled Computing Machinery and Intelligence, which opened with a question that still resonates. Can machines think? This seems straightforward, but Turing immediately identified the problem. What does think mean? How would you test whether a machine is thinking? Consciousness is subjective, internal, inaccessible from the outside. You can't peer into a machine and see thoughts the way you can disassemble it and see gears. Turing proposed a practical test. Put a human and a machine in separate rooms. An interrogator communicates with both via text, asking questions, receiving answers. If the interrogator can't reliably tell which responses come from the human and which from the machine, then the machine has passed the test. Not because it's proven to be conscious, but because it's indistinguishable from a conscious entity in its behavior. This became known as the Turing test, and it's been debated ever since. Is it a good test for intelligence? Does behavioral equivalence prove consciousness? Can a machine that merely simulates understanding actually understand? Turing anticipated objections. Some argued machines could never truly think because they're deterministic, following fixed rules. Turing countered that human brains might be deterministic too. Some claimed machines lack creativity. Turing noted that programs could generate surprising novel outputs. Some insisted consciousness requires a soul, something beyond physical matter. Turing replied that this was a theological claim, not a scientific one. The Turing test isn't perfect. Modern chatbots can pass limited versions of it without anything we'd recognize as understanding. They manipulate patterns in language convincingly without grasping meaning. But Turing's deeper point remains. If we can't tell the difference between intelligence and its simulation, maybe the distinction doesn't matter. Or maybe it does. Maybe there's something essential about consciousness, about subjective experience, that behavioral tests can't capture. This debate continues. What's undeniable is that Turing framed the question in terms that made it scientifically tractable. Not, do machines have souls, but can machines behave indistinguishably from thinking entities? The first question is metaphysics. The second is engineering. Turing died in 1954, at age 41, under circumstances still debated. He was prosecuted for homosexuality, which was illegal in Britain at the time, and subjected to chemical castration as an alternative to prison. 2 years later, he was found dead from cyanide poisoning. The official ruling was suicide. Some have questioned this, suggesting accidental poisoning from his amateur chemistry experiments. We'll never know with certainty. What's certain is that Turing left an intellectual legacy that shaped the modern world. He defined computation. He proved its limits. He designed stored program machines. He pioneered artificial intelligence research. He made thinking about thinking machines scientifically respectable. The Turing machine, that simple abstraction of tape and symbols, captures the essence of what all computers do. Every program, no matter how complex, can be reduced to a sequence of simple steps. Every algorithm, no matter how sophisticated, is ultimately just moving symbols according to rules. This is both humbling and empowering. Humbling because it suggests that human thought might also be mechanizable, that consciousness might be computation. Empowering because it means we can build machines that think, or at least machines indistinguishable from thinking ones. Turing proved that universal computers were possible in theory. But theory and reality are different things. Proving something can exist and actually building it require different tools. Turing showed the way with mathematics. Now we needed engineers to make it real with metal, wire, and eventually silicon. We needed switches, billions of them, small, fast, reliable, and cheap. We needed to learn how to organize those switches into processors, memory, circuits that could fetch instructions, decode them, execute them. We needed to transform Turing's abstract machine into something you could hold, something that ran on electricity instead of imagination. That transformation from theory to transistors is where we're heading next. From switches to silicon. Turing proved that thinking machines were possible. The mathematics was elegant, the logic unassailable. But mathematics doesn't care about friction, heat, or manufacturing tolerances. Reality does. Building an actual universal computer required the solving problems that pure theory never encounters. How do you make switches that don't wear out? How do you make them fast enough to be useful? How do you make enough of them without bankrupting yourself? The first computers weren't built from theory. They were built from desperation. In the early 1940s, the United States military had a problem. Artillery, large guns firing shells over long distances, required extensive calculations to aim accurately. You had to account for distance, angle, wind, air resistance, the rotation of the Earth, even temperature and humidity. Each combination of gun, shell, and conditions required its own entry in firing tables, books that gunners consulted in the field. These tables were calculated by hand. Teams of mathematicians, mostly women, worked with mechanical calculators, spending hours on each trajectory. A single table might require weeks of labor. The military needed hundreds of tables. The work was tedious, error-prone, and couldn't keep pace with the development of new weapons. The University of Pennsylvania received funding to build a machine that could calculate trajectories automatically. The team, led by John Mauchly and J. Presper Eckert, began work in 1943. 3 years later, they completed ENIAC, the electronic numerical integrator and computer. ENIAC was a monster. It weighed 30 tons. It occupied 800 square feet of floor space, roughly the size of a large apartment. It contained 17,468 vacuum tubes, 7,200 crystal diodes, 1,500 relays, 70,000 resistors, and 10,000 capacitors. 5 million hand-soldered joints connected everything together. When powered on, it drew 150 kilowatts, enough to dim lights across the neighborhood. Vacuum tubes were the key components, the switches that made electronic computation possible. A vacuum tube is a glass envelope containing metal elements in a near vacuum. Heat a cathode, and it emits electrons. Apply voltage to a grid between the cathode and anode, and you can control whether electrons flow. The tube acts as a switch. Voltage on the grid, current flows. Voltage off, current stops. This switching happened fast, far faster than mechanical relays. Vacuum tubes could switch thousands of times per second. ENIAC could perform 5,000 additions or 357 multiplications per second. Calculations that took humans days were completed in minutes. For the first time, a machine could outthink humans at mathematical reasoning, at least for certain kinds of problems. But vacuum tubes had serious drawbacks. They were fragile. Drop one, and it shattered. They generated enormous heat. ENIAC required industrial cooling fans to prevent overheating. They consumed substantial power, and they burned out. The filament inside each tube would eventually fail, just like a light bulb. With nearly 18,000 tubes in ENIAC, failures were constant. On average, a tube burned out every 2 days. Keeping ENIAC running required a team of engineers constantly replacing failed components. ENIAC had another limitation. It wasn't truly programmable in the modern sense. To change what it calculated, you had to physically rewire it. Programming meant setting hundreds of switches and reconnecting dozens of cables. This took hours or days. Betty Jennings, one of the original ENIAC programmers, described crawling inside the machine, tracing circuits, debugging by physically following the path electricity took through the hardware. The women who programmed ENIAC, Betty Jennings, Betty Snyder, Marlynn Westkoff, Kay McNulty, Frances Belis, and Ruth Lichterman, were brilliant. They had to understand the hardware at the deepest level because the hardware was the program. There was no separation. They invented programming techniques, developed debugging methods, created the first subroutines. But for decades, their contributions were overlooked. When ENIAC was unveiled to the press, the women weren't mentioned. The machine was presented as if it programmed itself. The problem of rewiring for each new program was obvious to everyone involved. John von Neumann, a Hungarian-American mathematician consulting on ENIAC, proposed a solution. Store the program in memory alongside the data. Don't hardwire instructions into the machine's physical configuration. Instead, treat instructions as numbers. Read them from memory. Execute them. Move to the next. To change what the computer does, load different numbers into memory. This is the stored program architecture, the foundation of every modern computer. Programs aren't built into hardware. They're data, patterns of numbers that tell the hardware what to do. The machine reads an instruction from a memory address, decodes what operation it specifies, executes that operation, and increments to the next address. This cycle, fetch, decode, execute, repeats billions of times per second in modern processors, but the principle remains unchanged from von Neumann's 1945 design. Von Neumann wrote a document describing this architecture for EDVACs, the successor to ENIAC. The report circulated widely and influenced every computer built afterward. Later, there was controversy about credit. Von Neumann's name became attached to the architecture, but Eckert and Mauchly had been thinking along similar lines. Turing, working independently in Britain, developed the same concepts. The idea was, in some sense, inevitable once people started thinking seriously about general-purpose computation. The stored program concept enabled something profound: software. Previously, changing a machine's function meant rebuilding it. Now, you just loaded different instructions. The hardware remained constant. The behavior changed because the numbers in memory changed. This separated the machine from its task, creating a distinction between physical computer and abstract program that defines computing to this day. But vacuum tubes still limited what was possible. They were too large, too hot, too unreliable, too power-hungry. Computers remained room-sized installations affordable only to governments and large corporations. The idea of personal computing seemed absurd. Why would an individual need a machine that filled a room and required a dedicated power supply? The breakthrough came from an unexpected place. Bell Telephone Laboratories, the research arm of AT&T. Bell Labs wasn't trying to build computers. They were trying to improve telephone systems. The telephone network in the 1940s used electromechanical switches, relays, to route calls. These were mechanical devices with moving parts that physically connected circuits. They worked but had limitations. They wore out. They were slow. They consumed space and power. Bell Labs wanted something better. In 1947, three researchers, John Bardeen, Walter Brattain, and William Shockley, demonstrated a new kind of switch made from a semiconductor material called germanium. They called it a transistor, short for transfer resistor. It had no vacuum, no moving parts, no filament to burn out. It was solid state, just a piece of germanium with carefully added impurities and attached wires. The first transistor was crude, fragile, unreliable. But the principle was sound. Semiconductors conduct electricity better than insulators, but worse than conductors, hence the name. By carefully controlling their structure and adding impurities, you could create regions with different electrical properties. Bring these regions together in the right configuration, and you could make a switch, a device where small voltages control larger currents. The physics is quantum mechanical, involving how electrons behave in crystalline solids, energy bands, and charge carriers. But the practical result is simple. Transistors can amplify signals and act as switches. Apply voltage to one terminal. Current flows between two others. Remove voltage. Current stops. It's an electrically controlled switch, just like a vacuum tube, but smaller, more reliable, and consuming far less power. Bell Labs initially used transistors in telephone systems, improving reliability and reducing size, but others saw wider applications. The first transistor radio appeared in 1954, portable and battery-powered, something impossible with vacuum tubes. Hearing aids, previously bulky devices with vacuum tubes and large batteries, became small enough to hide behind the ear. For computers, transistors were revolutionary. They were smaller, allowing more components in less space. They were more reliable, reducing maintenance. They consumed less power, reducing cooling requirements, and they switched faster than vacuum tubes, enabling quicker computation. The second generation of computers, built in the late 1950s and early 1960s, used transistors instead of vacuum tubes. These machines were smaller, faster, cheaper to operate, and more reliable. But they were still room-sized, still expensive, still requiring specialized facilities. The next breakthrough came from realizing that building transistors individually was inefficient. Each transistor had to be manufactured separately, tested, and then soldered by hand into circuits. The connections between transistors, the wires linking them, took more space than the transistors themselves. In 1958, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor independently developed a solution. Build multiple transistors on a single piece of semiconductor material, with the connections between them formed in the same manufacturing process. This was the integrated circuit, or microchip. Instead of assembling components, you could fabricate entire circuits at once. The process used photolithography, similar to photography. Coat a silicon wafer with light-sensitive material. Project patterns onto it using light and masks. The exposed areas harden or dissolve, depending on the chemistry. Etch away unwanted material. Add layers of insulators and conductors. Build up three-dimensional structures. Transistor by transistor, connection by connection, all through controlled chemical processes. This allowed unprecedented miniaturization. Early integrated circuits contained dozens of transistors. As manufacturing improved, that number grew. In 1965, Gordon Moore, who would co-found Intel, made an observation. The number of transistors you could fit on a chip seemed to double approximately every 2 years. This became known as Moore's Law. It's not a law of physics, but an empirical observation about manufacturing capability. Yet it held true for over 50 years. Doubling every 2 years is exponential growth. Start with 2,000 transistors in 1971, the number in Intel's first microprocessor. By 1991, you have 2 million. By 2011, 2 billion. Modern processors contain tens of billions of transistors on a chip smaller than your thumbnail. Each transistor is now measured in nanometers, billionths of a meter. The most advanced chips use transistors just a few nanometers across, smaller than most viruses, approaching the scale where individual atoms matter. Manufacturing at this scale requires extraordinary precision. The facilities, called fabs, cost billions of dollars. The processes involve hundreds of steps, each requiring exact control of temperature, pressure, chemical concentrations, and timing. But the result is astonishing. A modern processor contains more transistors than there are stars in the Milky Way galaxy, all packed into a few square centimeters, all switching billions of times per second, all manufactured for dollars instead of millions. This exponential growth in transistor count drove everything else. More transistors meant more memory, allowing programs to grow larger and more complex. More transistors meant faster processors, enabling real-time graphics, video processing, complex simulations. More transistors meant lower cost per function, making computers affordable first to businesses, then to hobbyists, finally to everyone. The computer you're using now, whether phone, tablet, or laptop, contains technology that would have seemed like magic to the engineers working on ENIAC. They would understand the principles. It's still switches, still Boolean logic, still fetch, decode, execute. But the scale, the speed, the miniaturization would be incomprehensible. ENIAC could perform 5,000 operations per second. A modern smartphone performs trillions. ENIAC weighed 30 tons. Your phone weighs a few ounces. ENIAC required 150 kilowatts. Your phone runs on a battery smaller than your palm. ENIAC cost nearly $500,000 in 1940s dollars, roughly $7 million in modern currency. Your phone costs a few $100s. This transformation from room-sized installations to pocket computers happened because we learned to make switches smaller, faster, cheaper, and more reliable. The switch is the fundamental unit of computation. Everything else is organization, pattern, abstraction. But you need the switches first. At the bottom of every computer, beneath the software and the operating systems and the user interfaces, there are transistors. Billions of them, carved into silicon, each one a tiny switch controlling the flow of electrons. Some are on, some are off. The pattern of on and off encodes everything. Your photos, your messages, your browsing history, your memories captured in digital form. We took sand, purified it to silicon, doped it with impurities to create semiconductors, carved patterns into it using light and chemistry, and created thinking machines. This is alchemy in the original sense, transmuting base materials into something that seems magical. Except the magic is physics, chemistry, and manufacturing precision. The hardware evolution from vacuum tubes to transistors to integrated circuits to modern processors is a story of miniaturization and multiplication. But having switches, even billions of them, isn't enough. They must be organized. They must be given structure. You need architecture, a blueprint for how switches connect and interact to form something that can fetch instructions, store data, perform calculations, and interface with the world. That architecture, the organizing principle that makes switches into computers, is where we're heading next. The von Neumann architecture. Imagine you have billions of switches. They're small, fast, reliable. You can turn them on and off millions of times per second. You can connect them in patterns that perform logic and gates, or gates, not gates, combinations that add numbers, compare values, store information temporarily. Now what? Switches alone don't make a computer any more than bricks alone make a cathedral. You need a plan, an architecture, a way of organizing components so they work together toward a purpose. You need to decide how information flows, where it's stored, how operations are sequenced, how the machine knows what to do next. This is the problem John von Neumann addressed in 1945. He'd been consulting on ENIAC, watching programmers spend days rewiring the machine for each new calculation. He'd read Turing's paper on computable numbers and understood that a truly universal computer needed to store its program in memory, treating instructions as data. But understanding the principle and designing a practical implementation are different challenges. Von Neumann wrote a document titled First Draft of a Report on the EDVAC, describing an architecture for a stored program computer. The report was incomplete, informal, meant for internal circulation among the team-building ENIAC's successor. But it leaked, circulated, and became foundational. Nearly every computer built since follows the principles von Neumann outlined, so much so that we call it the von Neumann architecture. The design has 5 main components: the arithmetic logic unit, the control unit, memory, input devices, and output devices. Together, these form a complete computing system capable of executing any algorithm that can be expressed as a sequence of instructions. The arithmetic logic unit, or ALU, is where computation happens. It performs basic operations: addition, subtraction, logical operations like AND, OR, NOT. These are the primitive operations from which all computation is built. Want to multiply? Perform repeated addition. Want to divide? Perform repeated subtraction. Want to compare 2 numbers? Subtract and check whether the result is 0, positive, or negative. The ALU is built from logic gates, which are built from transistors. An AND gate outputs 1 only if both inputs are 1. An OR gate outputs 1 if either input is 1. A NOT gate inverts its input. Combine these in the right patterns, and you get an adder, a circuit that takes 2 numbers in binary and produces their sum. Extend the adder, and you get circuits for subtraction, multiplication, comparison. Modern ALUs can perform dozens of operations, each implemented as a different circuit path through the gates. A control signal selects which operation to perform. Feed the ALU 2 numbers and an operation code, and it produces the result. It's fast, millions or billions of operations per second, but it's fundamentally simple. Each operation is just electricity flowing through carefully arranged transistors. The control unit orchestrates everything. It fetches instructions from memory, decodes what they mean, and directs other components to execute them. This is the brain of the computer, though even that metaphor is misleading. The control unit doesn't think. It follows predetermined patterns, but it coordinates the machine's behavior, making it seem purposeful. The control unit maintains a program counter, a register holding the memory address of the next instruction to execute. Each cycle, it fetches the instruction at that address, decodes it to determine what operation to perform and what data to use, executes the operation by sending appropriate signals to the ALU and other components, and then increments the program counter to point to the next instruction. This is the fetch, decode, execute cycle, the heartbeat of every computer. Fetch an instruction, decode it, execute it, move to the next. Repeat billions of times per second. Everything a computer does, from displaying graphics to playing sound to communicating over networks, reduces to this cycle repeated endlessly. Instructions can modify the program counter, creating loops and branches. An instruction might say, if the last ALU result was 0, set the program counter to address $1,000 instead of incrementing it normally. This allows conditional execution, doing different things depending on data. It's how computers make decisions, though decision implies consciousness the machine lacks. The machine just follows rules. If condition, then jump. The behavior appears intelligent only from outside. Memory is where everything lives. The program, the data, intermediate results, everything. In von Neumann's design, memory is a linear array of storage locations, each identified by an address. Think of it as a vast row of numbered boxes. Each box holds a number, or more precisely, a pattern of bits, ones, and zeros. The critical insight is that memory doesn't distinguish between instructions and data. Both are just numbers. The number 1000 might mean add if interpreted as an instruction, or it might mean the quantity 1000 if interpreted as data. The computer doesn't know or care. It reads numbers from memory and interprets them according to context. This flexibility is powerful. Programs can modify themselves, changing their own instructions during execution. One program can create another, writing instructions into memory that are later executed. A computer can simulate a different computer by treating that other computer's instructions as data, interpreting them step by step. Software becomes fluid, adaptable, infinitely flexible. But memory isn't monolithic. Modern computers have a hierarchy of memory types, each with different characteristics trading off speed, size, and cost. At the top are registers, tiny memory locations built directly into the processor. There might be only a few dozen registers, each holding a single number. But they're extraordinarily fast, accessible in a single clock cycle. The ALU operates on values in registers. The program counter is a register. Results are stored in registers before being written to larger memory. Next is cache, small but fast memory built into the processor chip or very close to it. Cache holds recently used data and instructions, exploiting the principle of locality. If you accessed something once, you'll likely access it again soon. Cache is measured in kilobytes or megabytes. It's made from the same transistor technology as the processor, which makes it expensive and limits how much you can include. Then comes main memory, or RAM, random access memory. This is measured in gigabytes. It's slower than cache, requiring dozens or hundreds of clock cycles to access. But it's much larger and cheaper per bit. RAM is volatile, meaning it loses its contents when power is removed. This is why unsaved work vanishes if your computer crashes. Beyond RAM is storage, hard drives or solid-state drives measured in terabytes. Storage is slower still, requiring milliseconds to access, millions of times slower than registers. But it's persistent. Turn off the power, and storage retains its contents. This is where programs and files live permanently. This hierarchy exists because of physics and economics. Fast memory requires transistors configured as latches, circuits that maintain a state as long as power flows. These take space and power. You can't build terabytes of register speed memory. It would be too large, too expensive, too power-hungry. So computers use small amounts of fast memory for immediate needs and larger amounts of slower memory for bulk storage, with intermediate cache levels bridging the gap. The speed difference matters enormously. Accessing RAM is roughly 100 times slower than accessing cache. Accessing storage is roughly 100,000 times slower than accessing RAM. If the processor had to wait for storage every time it needed data, it would spend most of its time idle. Cache hides this latency by keeping frequently used data close. When the processor needs something, the memory system first checks cache. If it's there, a cache hit, access is fast. If not, a cache miss, the system fetches it from slower memory, but also loads nearby data into cache, betting you'll need that too. Managing this hierarchy is complex. Hardware automatically moves data between levels based on usage patterns. Software can provide hints about what data will be needed next. The goal is to make slow memory appear faster by ensuring the processor usually finds what it needs in cache. Input and output devices connect the computer to the world. Input includes keyboards, mice, cameras, microphones, sensors, anything that feeds information into the system. Output includes screens, speakers, printers, network connections, anything that sends information out. I/O is handled through special instructions that read from or write to device addresses. To the processor, a device looks like a memory location. Write a number to address 5000, and maybe that number appears on screen. Read from address $6,000, and you get the latest key press. The details are hidden behind layers of abstraction, device drivers, operating systems, APIs. But fundamentally, I/O is just reading and writing numbers. This 5-component architecture, ALU, control unit, memory, input, output, is elegant in its simplicity. But it has a fundamental bottleneck, one von Neumann himself recognized. The processor and memory are separate. Every instruction must be fetched from memory. Every piece of data must be fetched from memory. Results must be written back to memory. The connection between processor and memory, called the memory bus, carries all this traffic, and it's limited in bandwidth. It can only transfer so much information per second. Modern processors can execute billions of instructions per second, but they can't fetch data that fast. Memory bandwidth can't keep up. The processor spends much of its time waiting for data, a problem called the von Neumann bottleneck. Engineers have developed clever solutions. Cache reduces the number of memory accesses. Pipelining allows the processor to work on multiple instructions simultaneously at different stages, fetching one while decoding another while executing a third. Prefetching tries to predict what data will be needed and loads it in advance. Multiple execution units work in parallel, performing independent operations simultaneously. But the fundamental bottleneck remains. Separating processing from storage means constant communication between them, and that communication is slow compared to how fast transistors can switch. Alternative architectures have been proposed, putting processing into memory or memory into processors, but none have displaced the von Neumann design. It's too well understood, too well supported by existing software, too deeply embedded in how we think about computing. The fetch, decode, execute cycle is simple enough to describe in a few sentences, but consider what it enables. Each instruction can perform a basic operation: add two numbers, compare values, load from memory, store to memory, jump to a different instruction. These operations are primitive, trivial individually, but chain them together. Thousands, millions, billions of instructions, and complexity emerges. A program to display a web page might execute billions of instructions, fetching data from storage, decompressing images, parsing HTML, calculating layout, rendering fonts, drawing pixels, all coordinated through sequences of simple operations. The program doesn't exist as a physical thing. It's a pattern of numbers in memory. Numbers interpreted as instructions by the control unit. Change those numbers, and the computer does something completely different. The hardware remains constant. The behavior changes because the pattern changes. This is the miracle of software. The same physical machine can be anything: a calculator, a word processor, a video player, a communication device, a game console, a music studio, a scientific instrument. Not because the hardware reconfigures itself, but because different numbers in memory direct it to behave differently. Von Neumann's architecture made this possible by treating programs as data, storing them in the same memory, allowing them to be loaded, modified, created, all through the same mechanisms used for any information. Programs became malleable, editable, transferable. You could copy a program as easily as copying a document. You could modify it, improve it, fix bugs, add features. Software became a thing that could be created, distributed, sold, shared, all independent of the hardware it ran on. This separation of hardware and software is so fundamental we barely notice it. But it's not obvious. Earlier, machines were hardware. Their function was determined by their physical construction. To change what they did, you rebuilt them. The stored program concept broke that connection, creating a distinction between the physical machine and its task. But there's still a problem. The machine operates on numbers, patterns of bits. Humans don't think in bits. We think in concepts, problems, goals. How do you tell a machine what to do when it only understands numbers and you only think in ideas? You need a way to translate human intentions into machine instructions, to bridge the gap between how we think and how computers operate. You need programming languages, compilers, operating systems, layers of abstraction that let us communicate with machines without having to speak their language of ones and zeros. That translation, from human thought to machine instruction, is where we're heading next. Speaking to machines. The von Neumann architecture provided a blueprint for organizing switches into a working computer. But it created a new problem. How do you tell this machine what to do? At the most fundamental level, computers understand only numbers. More precisely, they understand patterns of electrical voltage, high or low, 1 or 0, on or off. Everything a computer does must ultimately be expressed in binary, sequences of ones and zeros that the hardware interprets as instructions and data. A simple instruction might be rules. To the processor, this could mean add the contents of register 3 to register 5 and store the result in register 7. The exact meaning depends on the processor's design, its instruction set, the specific encoding chosen by the engineers who built it. But it's always numbers. Always binary. This is machine code, the native language of computers. It's what the processor actually executes, the only thing it directly understands, and it's utterly inhuman. Consider writing a program to add 2 numbers and display the result. In machine code, you'd specify, load the first number from a memory location into a register. Load the second number into another register. Add them using an ALU operation. Store the result to a memory location. Send that location's contents to the display device. Each step is a separate instruction. Each instruction is a pattern of bits, and you'd need to know the exact binary encoding for every operation. For a simple addition, This might be 20 or 30 instructions. For anything remotely complex, displaying graphics, playing sound, processing text, you'd need thousands or millions of instructions, each carefully encoded as binary numbers. Making a single mistake, one incorrect bit, could cause the entire program to crash or behave unpredictably. This is how the first programmers worked. They wrote programs in binary, using switches to set individual bits, checking and rechecking every number. It was tedious, error-prone, and required intimate knowledge of the hardware. Only specialists could do it, and even they made constant mistakes. The first improvement was assembly language. Instead of writing binary numbers, programmers wrote mnemonics, short abbreviations representing operations. ADD instead of 101, load instead of 11. MOV for move, JMP for jump, CMP for compare. Assembly language is still low level. Each assembly instruction corresponds directly to one machine instruction. You're still working at the level of individual operations, still manipulating registers and memory addresses directly. But at least the instructions are readable. ADD R3, R5, R7 is comprehensible in a way that 0, 1, 1 is not. An assembler translates assembly language into machine code. It's a simple translation, mostly a one-to-one mapping of mnemonics to binary codes with some handling of labels and addresses. This made programming less error-prone. You could read your code, understand what it did, find mistakes more easily, but it was still laborious. Complex programs required thousands of assembly instructions. The real breakthrough came with high-level programming languages. Languages that let programmers think in concepts rather than machine operations. Instead of specifying every register transfer and memory access, you could write X raise A plus B. The language understood variables, expressions, control structures. A compiler would translate this into the dozens or hundreds of machine instructions needed to actually perform the calculation. Fortran, developed at IBM in the 1950s, was one of the first widely used high-level languages. The name stands for Formula Translation. It was designed for scientific computing, letting researchers write mathematical formulas in notation resembling algebra, rather than machine instructions. A Fortran program to calculate trajectories might be a few dozen lines instead of thousands of assembly instructions. Programmers were initially skeptical. How could a mechanical translator produce code as efficient as handwritten assembly? Early compilers were crude, generating bloated, slow code. Experienced assembly programmers could write better code manually. But compilers improved. They learned optimization techniques, ways to rearrange operations, eliminate redundancy, use registers efficiently. Eventually, compilers became better than most humans at producing efficient machine code. Other languages followed. Lisp for artificial intelligence research, COBOL for business applications, C for system programming. Each had different strengths, different design philosophies, different ways of expressing computation. C, developed at Bell Labs in the early 1970s, struck a balance between high-level abstraction and low-level control. It provided structures for organizing code, functions, loops, conditionals, while still allowing direct memory manipulation when needed. C became the language of operating systems, the code that manages hardware and provides services to other programs. Unix, Windows, Linux, Mac OS, all are written primarily in C. Later languages went further from the machine. Python, developed in the late 1980s, emphasized readability and simplicity. A Python program looks almost like English. Variables don't need explicit type declarations. Memory management is automatic. The language hides most hardware details, letting programmers focus on logic rather than implementation. This abstraction comes at a cost. Python programs are slower than C, sometimes much slower. But for many applications, the slowdown doesn't matter. Computers are so fast that inefficiency is tolerable if it makes programmers more productive. A program that takes a second to run instead of a millisecond is still effectively instant from a human perspective. The translation from high-level language to machine code happens in two ways: compilation or interpretation. A compiler translates the entire program before execution. It reads your source code, analyzes it, checks for errors, performs optimizations, and produces an executable file containing machine code. Running the program means loading this executable and letting the processor execute it directly. This is how C and C++ work. The compilation step takes time, but the resulting program runs at full hardware speed. An interpreter works differently. It reads your source code line by line, translates each instruction into machine operations, and executes those operations immediately. Python uses this approach. There's no separate compilation step. You run the program, and the interpreter translates and executes on the fly. This is slower. Interpretation adds overhead, but more flexible. You can modify the program and immediately see results without waiting for compilation. Some languages use a hybrid approach. Java compiles to bytecode, an intermediate representation that's not machine code but closer to it than source code. The Java virtual machine then interprets or further compiles this bytecode. This provides portability. The same bytecode runs on any machine with a JVM, while recovering some of the performance lost to interpretation. These layers of translation create a remarkable property. The same program can run on different hardware. Write Python code on a Windows PC, and it runs unchanged on a Mac or Linux machine. The Python interpreter handles the differences, translating your code to whatever machine instructions the underlying processor requires. Software becomes portable, independent of hardware details. But languages and compilers only solve part of the problem. Even with high-level languages, you still need to manage hardware resources, allocating memory, accessing storage, handling input and output, scheduling tasks. Doing this in every program would be redundant and error-prone. This is where operating systems enter. An operating system is software that manages hardware on behalf of applications. It provides a layer of abstraction between programs and the physical machine, offering standardized services, file systems for organizing storage, memory management for allocating RAM, process scheduling for running multiple programs simultaneously, device drivers for communicating with hardware. When you save a file, you don't specify which physical sectors of the hard drive to write to. You tell the operating system to save the file, and it handles the details, finding free space, updating directory structures, managing caching. When you print, you don't send raw bytes to the printer. You tell the operating system to print, and it queues the job, communicates with the printer driver, handles errors. The operating system kernel is the core, privileged code with direct hardware access. It runs in a special processor mode with unrestricted permissions. Application code runs in user mode, restricted from directly accessing hardware. If an application needs hardware services, it makes a system call, asking the kernel to perform the operation on its behalf. This separation provides security and stability. A buggy application can't corrupt other programs' memory or crash the entire system. Each program runs in its own protected space. If it misbehaves, the operating system can terminate it without affecting anything else. This wasn't always true. Early personal computers ran one program at a time with full hardware access, and crashes often required rebooting. But modern operating systems enforce isolation. The operating system also provides multitasking, the illusion that many programs run simultaneously. In reality, on a processor with a single core, only one instruction executes at any moment. But the operating system rapidly switches between programs, running each for a few milliseconds before switching to another. The switching is so fast that it appears seamless. You can listen to music, browse the web, and edit a document simultaneously, though the processor is actually interleaving execution, spending a few milliseconds on each task in turn. On multi-core processors, true parallel execution is possible. Each core is an independent processor. A quad-core chip can literally run 4 instruction streams simultaneously. The operating system assigns tasks to cores, balancing load, managing communication between threads running on different cores. This parallelism makes computers faster, but it also makes programming harder. Coordinating parallel tasks, ensuring they don't interfere with each other. Avoiding race conditions where results depend on timing. These are subtle, difficult problems. Abstraction layers stack vertically. At the bottom, transistors implement logic gates. Gates combine to form ALUs, registers, memory. The processor executes machine code. Assembly provides mnemonics for machine code. High-level languages compile to assembly. Libraries bundle common functionality. Operating systems manage hardware. Applications use operating system services. Each layer builds on the one below, hiding details, providing simpler interfaces. This is why you can write a program without understanding transistors, why you can use a computer without knowing assembly language, why software written decades ago still runs on modern hardware through emulation and compatibility layers. Each abstraction hides complexity, allowing work at higher levels without drowning in low-level details. But abstraction has costs. Each layer adds overhead, slowing execution slightly. Each layer can introduce bugs or limitations. And abstraction can leak. Sometimes the underlying details matter, and you need to understand what's happening beneath the surface. Still, abstraction is essential. Without it, programming would be impossible at scale. The software running on your computer contains billions of lines of code written by thousands of programmers across decades. This is only possible because programmers work with abstractions, objects, functions, modules, libraries, rather than managing individual bits and transistors. Programming languages are human-designed tools for expressing algorithms in ways both humans and machines can understand. Different languages emphasize different values: performance, safety, ease of learning, expressiveness, portability. There's no single best language, only languages better or worse suited to particular tasks. C is excellent for operating systems and embedded systems requiring fine-grained control and maximum performance. Python excels at rapid prototyping and data analysis, where development speed matters more than execution speed. JavaScript runs in web browsers, enabling interactive web applications. SQL queries databases. Each language is a tool optimized for certain problems. Learning to program means learning to think algorithmically, to decompose problems into steps a computer can execute. The specific language matters less than the underlying concepts: variables, control flow, functions, data structures, algorithms. These are universal across languages. Learn them in one language, and you can apply them in others. But languages and operating systems, powerful as they are, remain tools for human programmers. They make programming easier. But programming is still hard. Writing correct, efficient, maintainable code requires skill, experience, creativity. It requires understanding both the problem you're solving and the tools you're using. It requires debugging when things inevitably go wrong, testing to ensure correctness, refactoring to improve clarity. The abstractions we've built, from machine code to assembly to high-level languages to operating systems, make it possible to communicate with machines. But they don't make it easy. They just make it possible at all. Without these layers, without these translations, computers would remain incomprehensible to all but a tiny elite of specialists. With them, millions of people can write software, creating the applications and systems that define modern computing. We've now seen how computers are built, how they're organized, and how we communicate with them. The hardware provides capability. The architecture provides structure. Languages provide expression. But having the means to tell a computer what to do raises a new question. What should we tell it to do? How do we describe solutions to problems in ways computers can execute? How do we write software that actually works? That's the art and craft of programming, and it's where we're heading next. Software and the art of programming. You now have the tools to communicate with a computer. High-level languages let you express ideas in human-readable form. Compilers translate those ideas into machine instructions. Operating systems manage hardware resources. The infrastructure exists. But writing software is more than translating ideas into code. It's problem-solving under constraints. It's designing solutions that work correctly, run efficiently, and can be understood and modified by others. It's an engineering discipline, a creative practice, and often an exercise in frustration. Programming is where the theoretical possibility of computation meets the messy reality of making things actually work. The process typically begins with a problem. You need software to track inventory, process images, analyze data, control a robot, display a website, play a game. The problem might be well-defined with clear requirements, or vague and evolving. Either way, you must transform the problem into a solution the computer can execute. This transformation happens in stages. First, you must understand the problem deeply enough to articulate what success looks like. What inputs will the program receive? What outputs should it produce? What are the edge cases, the unusual situations that might occur? What constraints exist? Speed, memory, accuracy? Then comes algorithm design. An algorithm is a precise, step-by-step procedure for solving a problem. It's a recipe, but more rigorous. Each step must be unambiguous. The sequence must terminate. No infinite loops unless intended. Given the same input, the algorithm should produce the same output reliably. For simple problems, the algorithm might be obvious. To find the largest number in a list, examine each number and keep track of the largest seen so far. To alphabetize words, compare them pairwise and swap those out of order, repeating until no swaps are needed. For complex problems, finding an algorithm is hard. How do you route packets through the internet efficiently? How do you compress a video file without losing too much quality? How do you recommend products a user might like based on their purchase history? These require insight, mathematical analysis, sometimes years of research. Once you have an algorithm, you implement it in code. This means choosing data structures, ways of organizing information in memory, and translating the algorithm's steps into programming language syntax. A list might be implemented as an array, a linked structure, or a tree, each with different performance characteristics. Choosing poorly can make the difference between a program that runs in seconds and one that takes hours. Writing the initial code is often the easy part. The hard part is debugging, finding and fixing errors. Bugs are inevitable. Even experienced programmers make mistakes constantly. You forget to check for empty input. You use the wrong comparison operator. You access an array element that doesn't exist. You create a loop that never terminates. You misunderstand what a library function does. The errors are endless and creative. Some bugs cause immediate crashes, making them relatively easy to locate. The program stops, often with an error message pointing to the problem location. Other bugs are subtle. The program runs but produces wrong results, only under certain conditions. These are insidious. The program appears to work during testing but fails in production with real data. Debugging is detective work. You form hypotheses about what's wrong. Test them by adding diagnostic output or running the program step by step in a debugger. Observe what actually happens versus what you expected, and refine your hypothesis. Sometimes the bug is where you think. Often it's somewhere else entirely. A wrong assumption you made early in the design. There's a psychological challenge to debugging. You must confront the fact that your code is wrong, that your reasoning was flawed. Novice programmers often blame the compiler, the operating system, the hardware, anything but their own logic. Experienced programmers know that the computer is almost certainly doing exactly what you told it to do. The problem is that you told it to do the wrong thing. This requires humility and systematic thinking. Emotional attachment to your code makes debugging harder. You must be willing to question every assumption, test every hypothesis. Throw away code that doesn't work even if you spent hours writing it. Testing is the systematic search for bugs. You run the program with various inputs, checking that outputs match expectations. For simple programs, you might test manually, trying different cases, seeing what happens. For complex programs, you write automated tests, code that runs other code and verifies correctness. Good testing requires imagining how the program might fail. What if the input is empty? What if it's extremely large? What if it contains special characters? What if two operations happen simultaneously? Thinking adversarially, trying to break your own program reveals bugs before users encounter them. But testing can only show the presence of bugs, not their absence. You can't test every possible input. For a program accepting two 32-bit integers, there are 2 power 64 possible input combinations, over 18 quintillion. Testing a tiny fraction proves little about the rest. Some bugs hide in rare combinations you never think to test. This is why correctness is hard. Mathematical proof of program correctness is possible for small programs with formal specifications, but impractical for large systems. Most software is verified through testing, code review, and operational experience, running it in production and fixing problems as they arise. Beyond correctness, programs must be maintainable. Software changes constantly. Requirements evolve. Bugs are discovered. New features are added. Performance must be improved. If the original programmer leaves, someone else must understand the code well enough to modify it. This makes clarity crucial. Code that works but is incomprehensible is problematic. Comments explain why code does something when the how is unclear. Variable names should be descriptive. Total or price communicates more than TP. Functions should have single, clear purposes. Complex logic should be broken into smaller, understandable pieces. There's an aesthetic to good code, a sense of elegance when a solution is expressed cleanly. Simple is better than complex. Clear is better than clever. Code that's easy to read is easier to debug, easier to modify, easier to trust. This isn't about personal preference. It's about long-term maintainability and reducing the cognitive load on whoever reads the code next, including your future self. Large programs are never written by one person. They are collaborative efforts involving teams of programmers, sometimes thousands of people across years or decades. This requires coordination, standards, communication. Version control systems track changes to code over time. Multiple programmers can work on different parts simultaneously without overwriting each other's changes. If a change introduces a bug, you can revert to an earlier version. You can see who changed what, when, and why. Git, the most widely used version control system, manages this complexity, allowing distributed teams to collaborate on software projects. Code reviews, where programmers examine each other's code before it's merged into the main codebase, catch bugs and enforce standards. A second pair of eyes often spots problems the original author missed. Reviews also spread knowledge across the team. Seeing how others solve problems teaches techniques you might not discover alone. Libraries and frameworks are collections of reusable code solving common problems. Why write your own sorting algorithm when the standard library provides one, tested and optimized? Why build a web server from scratch when frameworks handle routing, sessions, security? Standing on the shoulders of giants, using code others have written, lets you focus on the unique aspects of your problem rather than reinventing solutions. But dependencies create risk. Libraries might have bugs, security vulnerabilities, incompatibilities. A library you depend on might stop being maintained. A change in a library might break your code. Dependency management, choosing libraries carefully, keeping them updated, understanding what they do, is part of software engineering. Open source software, code published publicly for anyone to use and modify, has become foundational to modern computing. Linux, the operating system running most web servers and phones, is open source. Python, JavaScript, countless libraries and tools, all open source. Programmers contribute improvements, fix bugs, add features, all voluntarily or as part of their jobs. This collaborative model produces robust software through many eyes reviewing code, many users testing it, many developers improving it. It also creates commons resources anyone can use without licensing fees. The economics are sometimes puzzling. Why give away valuable work? But the model succeeds because contributors gain reputation, because companies benefit from improvements others make, because having widely used software is often more valuable than selling it. Software engineering extends beyond writing code. It includes requirements gathering, design, testing, documentation, deployment, monitoring, maintenance. In large organizations, these are often separate roles. Not all programmers write production code. Some write tests, some manage infrastructure, some design systems, some ensure security. Security is increasingly critical. Software vulnerabilities allow attackers to steal data, take control of systems, disrupt services. Writing secure code means thinking like an attacker, imagining how input might be crafted to cause unintended behavior. Buffer overflows, where data exceeds allocated space and overwrites adjacent memory. SQL injection, where malicious input is interpreted as database commands. Cross-site scripting, where attacker-controlled code runs in users' browsers. The catalog of vulnerabilities is extensive, and defending against them requires constant vigilance. Performance optimization is another specialized skill. Most code doesn't need to be perfectly efficient. Computers are fast enough that inefficiency rarely matters. But sometimes performance is critical. Processing millions of transactions per second, rendering graphics at 60 frames per second, training machine learning models on massive datasets. Optimization requires measurement. You must identify bottlenecks, the parts of the code consuming most resources. Optimizing the wrong sections wastes time. Profilers measure where programs spend time, revealing what actually needs improvement. Then you apply techniques, better algorithms, more efficient data structures, parallel execution, caching, reducing memory allocations. There's a saying, premature optimization is the root of all evil. Optimizing before you know whether it's needed often makes code more complex without meaningful benefit. Write correct, clear code first. Measure performance. Optimize only what measurements show is actually slow. Programming paradigms offer different ways of structuring programs. Procedural programming organizes code as sequences of instructions modifying state. Object-oriented programming groups data and functions into objects representing real-world entities. Functional programming treats computation as evaluating mathematical functions, avoiding changing state. Each paradigm suits different problems, and modern languages often support multiple paradigms. These are tools, not religions. The best approach depends on context. Object-oriented design works well for graphical interfaces and simulations. Functional programming excels at parallel computation and data transformation. Procedural code is straightforward for scripts and simple utilities. Skilled programmers choose appropriate tools rather than dogmatically adhering to one paradigm. The creative aspect of programming comes from design choices. There are many ways to solve any problem. Different solutions trade off between simplicity, performance, flexibility, maintainability. Choosing well requires experience, judgment, sometimes intuition. Good programmers develop taste, a sense of what makes one solution better than another beyond mere correctness. They recognize patterns, situations they've encountered before, where certain approaches work well. They anticipate future needs, designing systems that can evolve without requiring complete rewrites. But they also know when to keep things simple. Over-engineering, building more complexity than needed, is a common mistake. Trying to anticipate every possible future requirement leads to complicated systems that are hard to understand and maintain. Better to solve the immediate problem well and refactor later if requirements change. Programming is fundamentally about managing complexity. Simple programs are easy to understand completely. As programs grow, hundreds, thousands, millions of lines of code, no one person can hold the entire system in their head. Complexity must be managed through abstraction, modularity, clear interfaces, documentation. Large code bases are like cities. No single person understands every building, every street. But the city functions because there's organization, standards, infrastructure. Similarly, large software projects function because code is organized into modules with clear responsibilities. Interfaces define how modules interact. Conventions ensure consistency. Yet, despite all the engineering discipline, programming retains a creative element. The satisfaction of solving a difficult problem elegantly. The pleasure of writing in code that works beautifully. The joy of building something useful that didn't exist before. There's also frustration. Hours spent tracking down an elusive bug. Fighting with poorly documented libraries. Discovering that your carefully designed solution doesn't work as expected. Programming can be maddening, and tolerance for frustration separates those who persist from those who quit. But when it works, when your code does what you intended, when users benefit from software you created, there's genuine satisfaction. You've translated ideas into reality, transforming abstract algorithms into concrete functionality, making computers do things they couldn't do before. The tools, languages, compilers, operating systems, make programming possible. But the craft, understanding problems, designing solutions, writing clear code, testing rigorously, collaborating effectively, makes programming good. These skills that take years to develop and are never fully mastered. Even expert programmers constantly learn, adapting to new languages, frameworks, paradigms. We've now covered how to express solutions in code, how to build working software. But good code is more than correct. It must also be efficient, elegant, solving problems in ways that use computational resources wisely. That requires understanding algorithms not just as procedures, but as mathematical objects with properties we can analyze and compare. That's where we're heading next. The science of algorithms, the art of finding good solutions, and the limits of what can be computed efficiently. Algorithms, recipes for thought. Programming languages give you syntax. Software engineering gives you process. But neither tells you how to solve problems well. That requires algorithms, precise procedures that transform inputs into outputs, step-by-step recipes for computation. The word algorithm comes from the name of a 9th century Persian mathematician, Muhammad ibn Musa al-Khwarizmi, whose work on arithmetic and algebra introduced systematic methods for calculation to medieval Europe. An algorithm, in his sense, was a procedure. To solve this type of equation, perform these steps in this order. The concept is ancient. Euclid's algorithm for finding the greatest common divisor of two numbers dates to 300 BCE. It's still taught today because it's elegant and efficient. Given two numbers, repeatedly replace the larger, with the remainder of dividing the larger by the smaller. When one number becomes 0, the other is the answer. Simple, precise, guaranteed to terminate. But what makes one algorithm better than another? If multiple procedures solve the same problem, how do you choose? The answer lies in efficiency. How much time the algorithm takes, how much memory it requires, how the resources needed grow as inputs get larger. An algorithm that works beautifully on 10 items might become impossibly slow on 1,000,000 items. Understanding this scaling behavior is crucial. Consider searching. You have a list of names and want to find whether a particular name appears. The simplest approach is linear search. Start at the beginning. Check each name in sequence until you find a match or reach the end. If the list has n items, you might need to check all n before concluding the name isn't there. This works, but it's slow for large lists. Searching a phone book with 1,000,000 entries might require 1,000,000 comparisons. There's a better way, but it requires the list to be sorted. Binary search exploits order. Start in the middle. If the middle name matches, you're done. If your target comes alphabetically before the middle, search the first half. Otherwise, search the second half. Repeat, having the search space each time. With each comparison, you eliminate half the remaining items. After one comparison, 500,000 items remain. After two, 250,000. After 20 comparisons, you've narrowed it to about one item. Binary search on 1,000,000 items requires at most 20 comparisons. Linear search might need 1,000,000. This is the power of a better algorithm. Not a faster computer, not more efficient code, but a fundamentally smarter approach that reduces the work required. The difference becomes dramatic as data grows. Double the list size, and linear search takes twice as long. Binary search takes one additional comparison. With 1,000,000,000 items, linear search might need 1,000,000,000 comparisons. Binary search needs about 30. Measuring this scaling behavior requires mathematical notation. Computer scientists use big O notation to describe how an algorithm's resource requirements grow with input size n. Linear search is ON, pronounced order n, or big O of n. The time grows linearly with n, double the time. Binary search is O log n, where log means logarithm. The time grows logarithmically, increasing slowly even as n becomes enormous. The notation ignores constant factors. An algorithm taking exactly 5n steps is still ON, as is one taking n2 steps. What matters is the shape of growth: linear, logarithmic, quadratic, exponential. Constant factors affect performance but don't change how the algorithm scales. Some common complexity classes illustrate this. O1 is constant time. The operation takes the same time regardless of input size. Accessing an array element by index is O1. You jump directly to the location. The array could have 10 items or 10,000,000. Access takes the same time. O log n is logarithmic, like binary search. Doubling n adds just one more step. This scales beautifully. The difference between searching 1,000 items and 1,000,000,000 items is only about 10 times more comparisons. ON is linear. Processing each item in a list once is ON. If each item requires constant work, total time is proportional to n. Most simple loops over data are ON. ON log n appears in efficient sorting algorithms. Merge sort and quicksort both achieve this. They're faster than simpler sorts that are ON2, and for large datasets, the difference is massive. ON2 is quadratic. Nested loops where each item is compared to every other item produce this. Bubble sort, a simple sorting algorithm, is O(n)(2). For 100 items, that's 10,000 comparisons. For 1,000 items, 1,000,000 comparisons. Quadratic algorithms become impractical as data grows. O(2)n is exponential, and this is where things become hopeless. An algorithm that tries every possible subset of n items is O(2)n. With 10 items, that's 24 subsets. With 20 items, over 1,000,000. With 50 items, more than the number of atoms in the solar system. Exponential algorithms are only feasible for tiny inputs. These complexity classes reveal why some problems are fundamentally harder than others. It's not about clever coding or faster hardware. It's about the structure of the problem itself. Sorting illustrates the progression from naive to sophisticated algorithms. The simplest approach, selection sort, repeatedly finds the minimum element and moves it to the front. Each pass through the list finds one more element's final position. With n items, this takes n passes, each examining up to n elements, O(n)(2). For small lists, selection sort is fine. For large lists, it's painfully slow. Sorting 1,000,000 items could require 1,000,000,000,000 comparisons. Merge sort takes a different approach. Divide the list in half. Recursively sort each half. Merge the sorted halves together. The merging step is O(n). You walk through both halves once, picking the smaller element at each step. The recursion divides the problem log n times. Total complexity, O(n) log n. This is provably optimal for comparison-based sorting. You cannot sort in items faster than O(n) log n if your only operation is comparing pairs. Some algorithms achieve this bound: merge sort, quick sort, heap sort. They differ in details, memory usage, worst-case behavior, but all share the fundamental O(n) log n efficiency. Understanding why O(n) log n is optimal requires information theory. Sorting means determining which of the n factorial possible orderings is correct. With n items, there are nx, n factors 1, x, n 2, x, x 1 possible arrangements. Each comparison gives you one bit of information. Which of two elements is smaller? To distinguish among n possibilities requires log 2n bits of information, which is approximately n log n. You can't do better without additional information about the data. Some algorithms exploit additional structure. If you're sorting integers in a limited range, you can use counting sort, which is O(n)(n), but requires knowing the range ahead of time. If you know the data is nearly sorted, insertion sort performs well, running in nearly O(n) time. But for general comparison-based sorting, O(n) log n is the best possible. Algorithmic efficiency isn't just theoretical. It determines what's practical. Google searches billions of web pages. Linear search would take minutes per query. Sophisticated indexing and ranking algorithms, carefully optimized, return results in milliseconds. The difference between a usable service and an impossible one comes from algorithmic choices. Sometimes the best algorithm is surprising. Finding the shortest path through a graph, say the fastest route between cities, could naively try every possible path. For in cities, there are n. Paths, exponential complexity, utterly impractical. Dijkstra's algorithm solves this efficiently using a greedy approach. Start at the source. At each step, extend the shortest known path. Use a priority queue to track which node to expand next. The result is O(n) log en, with appropriate data structures, transforming an intractable problem into a routine calculation. The elegance of good algorithms comes from insight. Someone clever realized that you don't need to try every path, that expanding outward from the shortest known distances guarantees finding the overall shortest path. This insight, encoded as an algorithm, becomes a tool anyone can use. But not all problems have efficient algorithms. Some are fundamentally hard, requiring time that grows exponentially with input size no matter what approach you take. Others are suspected to be hard but haven't been proven so. This leads to one of the deepest questions in computer science. Does P equal NP? P is the class of problems solvable in polynomial time, roughly efficiently. Sorting, searching, shortest paths, all are in P. Their solutions scale as polynomials of input size, n, n2, n3. These are feasible even for large inputs. NP is the class of problems where solutions can be verified in polynomial time, even if finding solutions seems hard. Sudoku is NP. Given a filled grid, you can quickly check whether it's valid, but finding the solution might require trying many possibilities. The question is whether these classes are equal. If P plus NP, then every problem whose solution is easy to verify is also easy to solve. This seems unlikely. It feels like checking should be easier than solving. But nobody has proven they're different. This isn't just academic. Thousands of practical problems are NP complete, meaning if you solve one efficiently, you solve them all. Scheduling, routing, packing, circuit design, protein folding, all NP complete. A proof that PNP would confirm these problems have no efficient general solutions. A proof that P_NP would revolutionize computing, cryptography, and mathematics. Most computer scientists believe PNP, that some problems are inherently hard. But belief isn't proof. The question remains open, one of the Clay Mathematics Institute's Millennium Prize problems, with $1 million reward for solving it. For now, we live with NP-complete problems by using approximations, heuristics, and special cases. You can't always find the optimal solution quickly, but you can often find good enough solutions. Genetic algorithms, simulated annealing, local search. These techniques explore solution spaces intelligently without guaranteeing optimality. Sometimes approximate is sufficient. A delivery route that's 5% longer than optimal might be acceptable if finding the optimal route takes hours, and finding a good route takes seconds. Real-world constraints often favor fast, approximate solutions over slow, exact ones. Understanding algorithms changes how you think about problems. When faced with a computational challenge, experienced programmers don't immediately start coding. They consider algorithms. Is there a standard solution? What's the complexity? Can I reduce this to a solved problem? What are the trade-offs? They recognize patterns. This is a search problem. Use binary search if sorted. This is a shortest path problem. Use Dijkstra's algorithm. This is a matching problem. Use a maximum flow algorithm. Computer science provides a toolkit of algorithms, each suited to particular problem structures. They also recognize when problems are hard. If something feels like an NP-complete problem, you don't waste time searching for an efficient, exact algorithm. You accept approximation or try to find special structure that makes your particular instances easier. Algorithmic thinking extends beyond computers. Recipes are algorithms for cooking. Mathematical proofs are algorithms for establishing truth. Legal procedures are algorithms for resolving disputes. Any domain involving step-by-step reasoning can benefit from algorithmic analysis. The beauty of algorithms lies in their abstraction. An algorithm is independent of programming language, hardware, even physical implementation. Merge sort works the same whether implemented in Python or C, whether running on a phone or supercomputer. The logic is separate from the execution. This abstraction makes algorithms timeless. Euclid's algorithm works as well today as 2,300 years ago. The principles of binary search don't change with technology. Good algorithms are intellectual achievements, insights into problem structure that remain valid regardless of how computation evolves. We've now seen how to solve problems efficiently when efficient solutions exist. But what about problems where they don't? What are the fundamental limits of computation? What can't be computed even in principle? And what can be computed only with resources we'll never have? Those questions lead us to the deepest insights in computer science, the limits of what machines can do, the boundaries beyond which computation cannot go. That's where we're heading next. The limits of computation. Algorithms solve problems. Some problems have efficient solutions, sorting in O(n) log n, searching in O log n, finding shortest paths in polynomial time. Other problems seem harder, requiring exponential time, but we can still solve small instances. This might make you think that with enough computing power, eventually, everything becomes solvable. It doesn't. Some problems cannot be solved by any algorithm, no matter how much time or memory you have. Not because we haven't been clever enough to find the solution, but because no solution can possibly exist. Computation has fundamental limits, boundaries beyond which no machine can go. Alan Turing discovered the first of these limits in 1936 while investigating the foundations of mathematics. He asked whether there could be an algorithm to determine whether any given program would eventually halt or run forever. This is called the halting problem. It seems like a reasonable question. Sometimes you can tell by inspection whether a program halts. A loop that counts from 1 to 10 will obviously finish. A loop that continues while some variable is positive will halt if the variable eventually becomes 0 or negative. Surely there's some general method for analyzing any program and determining its behavior. Turing proved this is impossible. The proof is elegant and disturbing. Assume such an algorithm exists. Call it H for halt checker. Feed H a description of any program P and its input I, and H tells you whether P halts when given I or runs forever. Now construct a malicious program, call it paradox, that does the following. Paradox takes a program as input, runs H to check whether that program halts when given itself as input. If H says yes, it halts, then Paradox deliberately enters an infinite loop. If H says no, it runs forever, then Paradox immediately halts. What happens when you run Paradox on itself? Feed Paradox to Paradox. H must predict whether Paradox halts when given Paradox as input. If H predicts that Paradox halts, then by construction, Paradox doesn't halt. It enters the infinite loop. If H predicts Paradox runs forever, then Paradox halts immediately. Either way, H is wrong. This is a contradiction. The assumption that H exists leads to logical impossibility. Therefore, no such algorithm can exist. The halting problem is undecidable. This isn't a statement about current technology or human ingenuity. It's a mathematical proof that certain problems cannot be solved algorithmically. Not now, not ever, not even in principle. No matter how fast computers become, no matter how sophisticated our programming techniques, we cannot build a general halting checker. The implications ripple outward. Many other problems reduce to the halting problem. If you could solve them, you could solve halting. Since halting is unsolvable, so are they. Determining whether two programs compute the same function. Undecidable. Determining whether a program will ever access a particular memory location. Undecidable. Proving whether arbitrary mathematical statements are true. Undecidable, as Turing showed while answering Hilbert's and Scheidung's problem. These undecidable problems aren't obscure corner cases. They touch practical software engineering. You cannot build a perfect debugger that always determines whether code has bugs. You cannot build a perfect optimizer that always produces the fastest possible equivalent program. You cannot build a perfect security analyzer that detects all vulnerabilities. The problems are mathematically impossible. This forces a shift in perspective. We cannot solve all computational problems, so we must focus on the ones we can solve and understand the boundaries. Some problems are tractable. Others are hard but approximable. Some are impossible. Between solvable and impossible lies a vast territory of problems we can solve, but only slowly. These are the NP problems, and understanding their structure reveals deep connections between computation, logic, and the physical universe. P is the class of problems solvable in polynomial time. Time proportional to n high k for some constant k, where n is the input size. Polynomial time is considered efficient because it scales manageably. Even n3 becomes feasible with modern computers for moderately large n. Sorting, searching, graph traversal, matrix multiplication, all are in PNP is the class of problems where proposed solutions can be verified in polynomial time. Sudoku is NP. Given a completed grid, checking whether it follows the rules takes polynomial time. But finding the solution might require trying exponentially many possibilities. Here's the mystery. We don't know whether P equals NP. Does every problem with efficiently checkable solutions also have an efficient algorithm for finding solutions? Intuitively, this seems unlikely. Checking feels easier than solving, but nobody has proven they're different. The question matters enormously. Thousands of important problems are NP complete, meaning they're all equivalent in a precise sense. If you find an efficient algorithm for any NP complete problem, you've solved them all. Conversely, if you prove one has no efficient algorithm, they all lack efficient algorithms. Scheduling is NP complete. Given tasks with dependencies and deadlines, find a schedule that completes everything on time. Airlines, manufacturers, universities all face scheduling problems. Optimal solutions are critical, but finding them is hard. The traveling salesman problem is NP complete. Given cities and distances between them, find the shortest route visiting each city exactly once. This has applications in logistics, circuit board drilling, DNA sequencing. For small numbers of cities, you can try all routes. For 100 cities, there are more routes than atoms in the universe. Boolean satisfiability, or SAT, is NP complete. Given a logical formula, determine whether there's an assignment of true and false to variables that makes the formula true. This seems abstract, but has practical applications in circuit verification, software testing, and AI planning. The existence of NP-complete problems was discovered by Stephen Cook in 1971 and independently by Leonid Levin. Cook proved that SAT is NP-complete. Richard Karp then showed that many other problems reduce to SAT, establishing a large class of equivalently hard problems. If P, NP, all these problems have efficient solutions. Scheduling becomes easy. Optimization becomes trivial. Cryptography breaks. Current encryption relies on problems believed to be hard. The entire structure of computational difficulty collapses. Most computer scientists believe PNP. The intuition is strong that checking is fundamentally easier than solving, that some problems require exploring exponentially many possibilities. But intuition isn't proof. The question remains open, one of the most important unsolved problems in mathematics and computer science. For practical purposes, we assume PNP and work around it. When facing NP-complete problems, we use heuristics, algorithms that work well in practice without guaranteeing optimality. Simulated annealing mimics physical cooling processes to find good solutions. Genetic algorithms evolve solutions through mutation and selection. Local search explores nearby solutions, climbing toward better ones. These approaches don't solve NP-complete problems efficiently in the worst case. But real-world instances often have structure that makes them easier than the worst case. A scheduling problem for a real factory might be solvable even though the general problem is NP-complete. Practical SAT solvers can handle formulas with millions of variables by exploiting patterns in real instances. There's also approximation. For some NP-complete problems, you can find solutions guaranteed to be within a factor of optimal. A route that's at most 1.5 times the shortest possible can be found efficiently. This doesn't solve the problem exactly, but provides provable bounds on solution quality. Beyond NP lies even harder classes. PS-PACE contains problems solvable with polynomial memory, but potentially exponential time. EXP contains problems provably requiring exponential time. NAXP contains problems where even checking solutions requires exponential time. These hierarchies reveal that computational difficulty has structure. Problems organize into classes defined by resource requirements. Some classes are provably different. We know problems in EXP don't have polynomial time solutions. Others, like P versus NP, remain mysterious despite decades of effort. There are also problems that make NP look easy. Pressburger arithmetic, deciding truth of statements about integer addition, is provably harder than NP. The problem is decidable. Algorithms exist, but they require time proportional to 2 to n, double exponential. Even tiny inputs become infeasible. Chess and Go, played on finite boards, are technically decidable. There are only finitely many possible positions, so you could in principle enumerate them all and determine the perfect move. But the state space is so vast that this brute force approach is utterly impractical. Chess has roughly 10⁻120 possible positions. The universe contains about 10⁻80 atoms. Perfect play is computable in theory, but impossible in practice. This distinction between theoretical computability and practical feasibility is crucial. Many problems are computable but intractable. We can write programs that would solve them given infinite time and memory, but in reality, they'll never finish. The algorithm exists, but running it would require more resources than exist in the universe. Quantum computing potentially changes this landscape. Quantum computers exploit superposition and entanglement to explore multiple solution paths simultaneously. For certain problems, they provide exponential speedup. Shor's algorithm factors large numbers in polynomial time on a quantum computer, threatening current cryptography. Grover's algorithm searches unsorted databases quadratically faster than classical algorithms. But quantum computing doesn't solve all hard problems. NP-complete problems appear to remain hard even for quantum computers. The speedups are dramatic for specific problems, but don't fundamentally alter the computational hierarchy. Quantum computers are powerful new tools, not magical problem solvers that make all hard problems easy. Physical limits also constrain computation. The Bekenstein bound limits how much information can be stored in a finite region of space. The Margolis-Levitin theorem limits how fast quantum states can change, setting a maximum speed for computation. These aren't engineering limitations, but consequences of physics itself. Energy requirements matter too. Every irreversible computation generates heat through the Landauer principle. Erasing one bit of information requires a minimum energy dissipation. For reversible computation, energy can theoretically be arbitrarily low, but practical implementation faces enormous challenges. These physical constraints mean that even if p Sachen Rs NP, there are limits to what can be computed in our universe. A polynomial time algorithm requiring 10 nano-100 operations is theoretically efficient, but practically useless if running it would require more energy than the sun produces in its lifetime. The limits of computation are not merely technical obstacles to be overcome with better engineering. Some are mathematical, undecidable problems that no algorithm can solve. Some are computational, problems solvable in principle but requiring resources that grow faster than available. Some are physical, constraints imposed by the laws of the universe itself. Understanding these limits is humbling, but also clarifying. We cannot do everything, but within the vast space of what we can do, there's enormous room for creativity, optimization, and innovation. The problems we can solve efficiently enable modern computing. The problems we can approximate enable practical solutions to hard challenges. Even approaching the boundaries teaches us about computation, logic, and the structure of reality. We've now seen what computers can do efficiently, what they can do slowly, and what they cannot do at all. But computation isn't just about abstract problems. It's about information, representing it, storing it, transmitting it, transforming it. The next piece of the puzzle is understanding how computers encode and manipulate the raw material of computation itself. Data. Data and information. At the most fundamental level, computers manipulate data. Not ideas, not concepts, but patterns of ones and zeros. Electrical charges representing information. Everything you see on a screen. Every sound from speakers, every document, image, video, all of it is ultimately numbers. This seems impossible. How can a photograph be a number? How can music be binary? How can the complete works of Shakespeare reduce to a sequence of bits? The answer reveals something profound about information itself. It's independent of physical form. What matters isn't the medium, but the pattern. Consider text. The letter A isn't inherently anything. It's a shape we've agreed represents a particular sound and meaning. To store A in a computer, we assign it a number. In ASCII, the American Standard Code for Information Interchange developed in the 1960s, A is 65. The computer stores 65 as binary. Ho 1 ho zone zo 1. Each character gets a number. B is 66, C is 67, and so on. Lowercase letters have different codes. A is 97. Digits, punctuation, spaces all receive unique numbers. ASCII uses 7 bits per character, allowing 128 possible values, enough for English text and common symbols. This encoding is arbitrary but standardized. Everyone agrees that 65 means A, so text can be exchanged between systems. Store the numbers, and you've stored the text. The physical representation, electrical charges in RAM, magnetic domains on a hard drive, pits on an optical disc, doesn't matter. What matters is preserving the pattern. ASCII worked for English but not for languages with thousands of characters. Unicode, developed in the 1990s, solves this by assigning unique numbers to over 140,000 characters, covering virtually all written languages, plus emoji and special symbols. A is still 65 for compatibility, but now A, Greek alpha, has a code, as does Zhong, Chinese, A, Hebrew, emoji. Unicode uses variable length encoding. Common characters fit in 1 byte. Rare characters require more. UTF-8, the most common Unicode encoding, is backward compatible with ASCII while supporting the full character set. This allows text in any language to be represented digitally and exchanged globally. Numbers themselves are straightforward. Binary is a base 2 number system using only 0 and 1, unlike decimal space and 10 using digits 09. The number 13 in decimal is 1101 in binary, 18, 14, no 2s, 11. Each position represents a power of 2, 128, 64, 32, 16, 8, 4, 2, 1. Computers use binary because transistors have 2 states, on or off. Representing 10 states reliably would be difficult. 2 states are simple and robust. High voltage represents 1, low voltage represents 0. Everything else builds on this foundation. Integers are stored directly as binary. A 32-bit integer can represent values from 0 to about 4.3 billion, or with 1 bit reserved for sign, from about 2.1 billion to 2.1 billion. Need bigger numbers? Use 64 bits, allowing values up to 18 quintillion. Fractional numbers require different encoding. Floating point representation stores numbers in scientific notation, a significand, the significant digits, and an exponent, the scale. The number 1234.5 becomes approximately 1.2345 x 103. In binary floating point, you store the binary significand and binary exponent. This introduces limitations. Not all decimal fractions can be represented exactly in binary. The number 0.1 in decimal is a repeating fraction in binary, like 13 in decimal produces 0.333. Computers store approximations, introducing tiny errors. These errors accumulate in long calculations, which is why financial software uses special decimal representations rather than floating point. Images are arrays of pixels, each pixel a number representing color. Grayscale images assign each pixel a brightness value, typically 0 for black to 255 for white. Color images use 3 values per pixel: red, green, and blue intensities. Mix red, green, and blue light in different proportions, and you can produce millions of colors. A 1920s T80 image contains over 2 million pixels. At 3 bytes per pixel, 1 each for red, green, blue, that's about 6 megabytes uncompressed. Store the numbers, and you've stored the image. Display the numbers on screen by lighting pixels according to their values, and the image reappears. Sound is sampled pressure waves. Microphones convert air pressure variations into electrical voltage variations. Sample this voltage thousands of times per second, converting each sample to a number, and you've digitized the sound. CD-quality audio samples 44,100 times per second at 16 bits per sample, capturing frequencies up to 22,050 Hz, just beyond human hearing range. Video combines images and sound. A movie at 24 frames per second for 2 hours contains 172,800 images plus audio. Uncompressed, this would require terabytes. Compression makes it manageable. Compression exploits redundancy and irrelevance. Images often contain large areas of similar color. Instead of storing each pixel independently, store the color once and note which pixels share it. This is lossless compression. You can perfectly reconstruct the original. JPEG image compression is lossy. Discarding information human eyes barely notice. The human visual system is less sensitive to color details than brightness details. JPEG exploits this by storing color information at lower resolution than brightness. It also uses frequency analysis, keeping low-frequency components that define overall structure while discarding high-frequency details. The result is images 1/10 the original size with minimal perceptible quality loss. You can't reconstruct the exact original. Information was discarded, but the compressed version looks nearly identical. The trade-off between file size and quality is adjustable. MP3 audio compression uses similar principles. Human hearing is less sensitive to certain frequencies and can't hear quiet sounds masked by loud ones. MP3 analyzes audio frequency content and discards components unlikely to be heard. A 50 megabyte audio file might compress to 5 megabytes with little audible difference. Video compression combines spatial compression within frames and temporal compression between frames. Most frames in a video are similar to previous frames. Only small regions change. Instead of storing each frame completely, store the differences. Combined with image compression techniques, this reduces video to manageable sizes. Modern video codecs like H.264 achieve remarkable compression ratios through sophisticated algorithms analyzing motion, predicting future frames, and encoding only the differences. A 2-hour movie requiring terabytes uncompressed fits in a few gigabytes compressed, small enough for streaming. All compression algorithms face the same fundamental limit. You cannot compress random data. Compression works by finding patterns and redundancy. Truly random data has no patterns to exploit. This is formalized in information theory, developed by Claude Shannon in the 1940s. Shannon defined information as the reduction of uncertainty. A message with high information content tells you something unexpected. Predictable messages contain little information. Optimal compression reduces data to its information content, eliminating redundancy without losing meaning. Shannon's work established fundamental limits on compression and transmission. The entropy of data determines the minimum possible compressed size. You cannot compress below this limit without losing information. Real compression algorithms approach this theoretical optimum without quite reaching it. Encryption transforms data to hide its content from unauthorized access. Strong encryption makes data indistinguishable from random noise without the decryption key. This seems to contradict information theory. Encrypted data shouldn't compress well if it looks random. But you compress first, then encrypt. The compressed data contains the information. Encryption just scrambles it. Databases organize data for efficient access. Instead of storing information in files, databases structure it as tables, records, and fields with relationships between them. A customer database might have tables for customers, orders, and products, with links connecting orders to customers and products. Query languages like SQL let you retrieve information. Find all orders placed by customer 10345 in the last month. The database engine optimizes this query, using indices and efficient algorithms to locate relevant records quickly. For large datasets, millions of records, proper database design means the difference between instant results and waiting minutes. Indexing is crucial. An index is like a book's index, mapping search terms to locations. Without an index, finding a record requires scanning the entire database. With proper indices, the database jumps directly to relevant records. Creating and maintaining indices requires storage and processing time, but the speed up for queries is dramatic. Data integrity matters. Databases ensure that related information remains consistent. If you delete a customer, orders referencing that customer must be handled, either deleted or marked invalid. Transactions group multiple operations so they either all succeed or all fail, preventing partial updates that leave data in inconsistent states. The scale of modern data is staggering. Google processes petabytes daily, millions of gigabytes. Facebook stores hundreds of petabytes of photos and videos. The Large Hadron Collider generates petabytes of data annually from particle collisions. Analyzing this data requires distributed systems, spreading storage and computation across thousands of machines. Big data introduces new challenges. Traditional databases assume data fits on one machine. Distributed databases split data across many machines, requiring coordination to ensure consistency and handle failures. MapReduce and related frameworks parallelize computation, processing different data portions simultaneously and combining results. Machine learning algorithms discover patterns in massive datasets. Train a model on millions of images, and it learns to recognize objects. Feed it billions of words, and it learns language patterns. The algorithms are mathematical, optimizing parameters to minimize prediction error, but they require enormous data to work well. Data privacy and security become critical at scale. Leaked data can't be unleaked. Breaches expose millions of people's information: names, addresses, financial details, medical records. Organizations holding data have responsibilities to protect it, encrypt it, limit access, audit usage. Data also accumulates historical bias. If training data reflects societal inequalities, machine learning models learn and perpetuate those inequalities. Algorithmic decisions based on biased data can discriminate, denying loans or opportunities based on patterns that correlate with protected characteristics. These ethical dimensions of data are increasingly important. Data isn't neutral. How it's collected, stored, analyzed, and used has consequences. Privacy regulations like GDPR attempt to give individuals control over their data, requiring transparency about collection and use. But data's value lies in aggregation and analysis. Individual data points reveal little. Millions of data points reveal patterns, trends, predictions. This tension between individual privacy and collective insight has no easy resolution. Compression, encryption, databases, indices, distributed systems, machine learning, all are tools for managing information. At the foundation, everything is numbers. Text, images, sound, video, all encoded as binary patterns. The physical substrate doesn't matter. Magnetic domains, electrical charges, optical pits, whatever stores the pattern preserves the information. This abstraction is powerful. Information becomes fluid, copyable, transmittable, transformable. Copy a file, and you've duplicated information perfectly at near zero cost. This is unlike physical objects, where copying requires materials and labor. Digital information can be replicated infinitely without degradation. This property enables modern computing. Software is information. Copy it freely. Documents are information. Share them instantly. Knowledge is information. Distribute it globally. The marginal cost of duplicating information is effectively zero, which revolutionizes economics, culture, and society. But information in isolation has limited value. Information becomes powerful when connected, when computers communicate, when data flows between systems. The Internet transforms isolated computers into a global network, enabling information sharing at unprecedented scale. That network, how it works, how data traverses it, how billions of devices coordinate, that's where we're heading next. Networks and the Internet. A computer in isolation is useful. It can process data, run programs, store information. But connect computers together. Let them communicate. And something transformative happens. Individual machines become nodes in a network, sharing resources, exchanging information, coordinating tasks. The whole becomes vastly greater than the sum of its parts. The Internet is the largest machine humanity has ever built. Billions of devices spanning the globe, connected through cables, fiber optics, wireless signals, and satellites. Data flows between them constantly. Emails, web pages, videos, financial transactions, sensor readings, social media posts. The Internet has become infrastructure as fundamental as electricity or running water. But it started small, an experiment in connecting a handful of research computers. In the 1960s, computers were expensive, isolated machines. Universities and research labs owned a few, each serving many users through time sharing. If you wanted to use a computer at another institution, you traveled there or mailed them your program on punched cards and waited weeks for results. Sharing data meant physically transporting magnetic tapes. The U.S. Department of Defense's Advanced Research Projects Agency, ARPA, funded research into connecting computers across distances. The goal was resource sharing and resilience. If computers could communicate, users could access remote machines. If one computer failed, others could continue functioning. The challenge was how to connect diverse computers reliably over unreliable communication lines. Telephone networks existed, but were designed for voice, maintaining continuous circuits between endpoints. Computer communication is bursty. Periods of activity followed by silence. Dedicating a circuit for the entire duration of a computer session would waste bandwidth. The solution was packet switching, developed independently by Paul Baran in the U.S. and Donald Davies in the U.K. Instead of maintaining circuits, break data into small packets. Each packet travels independently through the network, routed from node to node toward its destination. Nodes store packets briefly, examine destination addresses, and forward them along appropriate paths. This design has remarkable properties. No single path is critical. If one route fails, packets take different roads. The network is decentralized with no central control point. Adding new nodes or connections doesn't require reconfiguring everything. The system is robust, flexible, scalable. ARPANET, the first packet-switched network, went live in 1969 connecting 4 sites: UCLA, Stanford Research Institute, UC Santa Barbara, and the University of Utah. The first message, sent from UCLA to Stanford, was supposed to be login, but the system crashed after LO. Even failures are part of the story. ARPANET grew steadily through the 1970s, connecting dozens of institutions. Protocols evolved, standardized rules for how computers communicate. TCP/IP, Transmission Control Protocol, HART's Internet Protocol, emerged as the standard, defining how packets are addressed, routed, and reassembled. IP, the Internet Protocol, handles addressing. Every device on the Internet gets an IP address, a unique number identifying it. The original IPv4 uses 32-bit addresses, allowing about 4.3 billion unique addresses. This seemed sufficient in the 1980s, but proved insufficient as the Internet exploded. IPv6 uses 128-bit addresses, enough for trillions of devices per person on Earth. IP addresses look like 192.168.1.1, 4 numbers separated by dots, each between 0 and 255. This is human-readable notation for 32-bit binary number. Devices use the binary form, humans use the dotted notation. TCP, Transmission Control Protocol, handles reliable delivery. IP alone just sends packets toward destinations with no guarantee they arrive in order, or arrive without errors. TCP adds acknowledgments, retransmission, ordering, error checking. When you request a web page, TCP ensures you receive all the data correctly despite packets potentially arriving out of order or getting lost. The combination, TCP/IP, became the foundation of the Internet. Other networks existed: corporate networks, academic networks, government networks, but they used incompatible protocols. The genius of TCP/IP was its simplicity and openness. Anyone could implement it. Any network could adopt it. In 1983, ARPANET switched to TCP/IP, creating the Internet as a network of networks. Other networks connected, forming a global system. The Internet isn't a single network, but thousands of networks choosing to communicate using common protocols. This distributed design means no one owns or controls the Internet. Organizations own individual networks. ISPs own infrastructure. Corporations own data centers. Individuals own home networks. But the Internet itself is a collective agreement to use TCP/IP and connect. The Domain Name System, DNS, maps human-readable names to IP addresses. Remembering 170.27.164.46 is difficult. Remembering Google.com is easy. DNS translates names to numbers, letting you type readable addresses while computers use numeric IPs underneath. DNS is hierarchical and distributed. Top-level domains like .com, .org, .edu are managed by designated organizations. Each domain can delegate subdomains. Google.com delegates mail.google.com, maps google.com. DNS servers worldwide cache translations, making lookups fast. When you visit a website, your computer asks DNS servers for the IP address, then contacts that address. With addressing and routing established, applications could use the Internet. Email predated the web, becoming the first killer app. Send messages to anyone with an email address anywhere on the Internet, delivered within seconds or minutes. Before email, communication meant phone calls, postal mail, or nothing. Email transformed business and personal communication. The World Wide Web, invented by Tim Berners-Lee at CERN in 1989, made the Internet accessible to non-technical users. Before the web, accessing Internet resources required knowing cryptic commands and protocols. The web introduced a simple model: documents linked together, accessed through URLs displayed in browsers. A web page is a document written in HTML, hypertext markup language, describing structure and content. Hyperlinks connect pages, creating a web of interconnected information. Browsers retrieve pages via HTTP, Hypertext Transfer Protocol, displaying them graphically. The web isn't the Internet. It's an application running on the Internet. But it became synonymous with the Internet for most users. Email, file transfer, video streaming, all use the Internet's infrastructure. But the web is what made the Internet mainstream. Understanding how a web page loads reveals the layers at work. You type a URL, www.example.com /page HTML. Your browser extracts the domain name, example.com, and queries DNS to get its IP address. DNS returns something like 93.102.1.6.34. Your browser establishes a TCP connection to that address on port 443, the standard HTTPS port. TCP performs a handshake. Your computer sends a SYN packet. The server responds with SYN ACK. Your computer replies with ACK. Connection established. Over this connection, your browser initiates an HTTPS session, encrypted communication preventing eavesdropping. Public key cryptography establishes a shared secret key. All subsequent communication is encrypted using this key. Your browser sends an HTTP GET request. Please send me page.html. The server retrieves the file, sends it back as an HTTP response. The data travels as packets through many routers between you and the server, each router examining the destination IP and forwarding packets toward it. Your browser receives the HTML, parses it, and discovers it references other resources: CSS style sheets, JavaScript files, images. For each, the browser makes additional HTTP requests, fetching resources, rendering them into the visual page you see. This entire process, DNS lookup, TCP connection, HTTPS negotiation, HTTP requests, packet routing, happens in milliseconds. The complexity is hidden. You just see a web page appear. The client-server model dominates Internet architecture. Clients, like your browser, request resources. Servers provide them. Email works this way. Your email client requests messages from a mail server. Streaming works this way. Your video player requests video data from streaming servers. Servers must handle many simultaneous clients. A popular website serves millions of requests per second from clients worldwide. Load balancers distribute requests across multiple server machines. Content delivery networks, CDNs, cache content geographically, serving requests from nearby servers rather than distant data centers. Encryption is critical for security. Without it, anyone between your computer and the destination can read your data. HTTPS encrypts web traffic. VPNs encrypt all traffic, creating encrypted tunnels through the Internet. This protects passwords, financial data, private communications from interception. Public key cryptography enables secure communication between strangers. Traditional encryption requires sharing a secret key first. But how do you share the key securely? Public key cryptography solves this. Each person has two keys, public and private. Anything encrypted with the public key can only be decrypted with the private key. You publish your public key freely. Anyone can encrypt messages to you that only you can decrypt. This also enables digital signatures. Encrypt a hash of a message with your private key. Anyone can decrypt with your public key, verifying the message came from you and hasn't been altered. This authenticates software, financial transactions, legal documents. The Internet's resilience comes from redundancy and decentralization. Data flows through multiple paths. If a cable breaks, routers find alternate routes. No single point of failure can take down the global Internet, though portions can be disrupted. This robustness extends to content. Files spread across peer-to-peer networks have no central server. Each participant downloads from and uploads to others. BitTorrent works this way. Popular files are served by thousands of users simultaneously, distributing bandwidth load and eliminating single points of failure. The cloud is just other people's computers. Cloud storage means uploading files to remote servers maintained by companies like Google, Amazon, Microsoft. Cloud computing means running programs on remote servers rather than local machines. The advantages are accessibility. Your files and applications are available from any device, and scalability. Providers handle hardware, redundancy, and capacity. But the cloud introduces dependencies. If the service fails, your access fails. If the company goes bankrupt, your data might vanish. If governments demand access, your privacy is compromised. The cloud offers convenience at the cost of control. Internet governance is decentralized but coordinated. ICANN manages domain name assignments. Regional registries allocate IP addresses. Standards bodies define protocols, but no single authority controls the Internet. This creates both resilience and challenges in addressing abuse, illegal content, and security threats. Cyber attacks exploit Internet vulnerabilities. Distributed denial-of-service attacks flood targets with traffic, overwhelming servers and making services unavailable. Botnets, networks of compromised computers, amplify attacks. Ransomware encrypts victims' files, demanding payment for decryption keys. Securing networked systems is an endless arms race. Firewalls filter traffic. Intrusion detection monitors for suspicious activity. Encryption protects data. But new vulnerabilities emerge constantly. Software bugs, configuration errors, social engineering all provide attack vectors. The Internet has transformed society in ways its creators never imagined. Global, instant communication, access to information, remote work, online commerce, social networks, all depend on billions of devices reliably exchanging packets. We've connected the world's computers into a single integrated system. Information flows globally in milliseconds. Knowledge is accessible anywhere. Communication transcends geography. This connectivity, built on simple protocols and distributed architecture, is perhaps computing's greatest achievement. But connecting computers is just infrastructure. What makes the Internet transformative is what we do with it, the applications, services, and increasingly, the intelligence we're building on top. Computers no longer just compute or communicate. They're beginning to learn, to recognize patterns, to make predictions. They're approaching something that looks like intelligence, though whether it's genuine remains debated. That's where we're heading next. Intelligence, learning, and the question of whether machines can truly think. Intelligence and learning machines. The dream of artificial intelligence is as old as computing itself. If machines can calculate, can they think? If they can process information, can they understand? If they can follow instructions, can they learn? For decades, these questions seemed philosophical, untestable speculation. Then, gradually, machines began doing things that looked intelligent, playing chess, recognizing speech, translating languages, driving cars, generating coherent text, creating realistic images. The capabilities expanded so rapidly that what seemed impossible a decade ago is now routine. But there's a persistent question beneath the achievements. Are these machines actually intelligent, or are they just very good at mimicking intelligence? Do they understand, or do they just process patterns? Is there genuine thought happening, or just sophisticated computation? The answer depends on what you mean by intelligence. Early artificial intelligence research, beginning in the 1950s, assumed intelligence meant logical reasoning. If computers could manipulate symbols according to rules, they could solve problems that required intelligence. Chess seemed like the perfect test, a game of pure logic requiring planning, strategy, evaluation of positions. In 1997, IBM's Deep Blue defeated world chess champion Garry Kasparov. The machine evaluated 200 million positions per second, searching many moves ahead, choosing the path with highest evaluated value. It played brilliantly, but it didn't understand chess. It didn't grasp strategy the way humans do. It calculated, it searched, it optimized. Whether that constitutes intelligence is debatable. Rule-based systems dominated early AI. Encode knowledge as rules. If X, then Y, and let the computer apply them. Expert systems captured knowledge from human experts. Medical diagnosis systems, financial planning systems, troubleshooting systems. They worked in narrow domains but were brittle. Unexpected situations broke them. They couldn't learn or adapt. The turning point came from a different approach. Instead of programming intelligence, let machines learn it from data. Machine learning algorithms discover patterns in data without being explicitly programmed. Show a learning algorithm thousands of cat photos labeled cat and thousands of non-cat photos labeled not cat, and it learns to distinguish cats from non-cats. Not through rules about whiskers and ears, but by finding statistical patterns in pixel values that correlate with the label. This seems almost magical. How can an algorithm learn concepts from examples? The answer is optimization. Fitting models to data by adjusting parameters to minimize prediction error. A simple example, linear regression. You have data points, say house sizes and prices. You want to predict price from size. Linear regression fits a line through the points by finding the slope and intercept that minimize the squared distance between the line and actual prices. The result is a model. Price slope, x size plus intercept. Give it a new size, and it predicts a price. This generalizes. Instead of lines, use complex functions with thousands or millions of parameters. Instead of predicting numbers, predict categories. Cat or not cat, spam or not spam, disease or healthy. Adjust parameters to minimize error on training data, and you have a model that makes predictions on new data. Neural networks, inspired loosely by biological brains, are particularly powerful learners. A neural network consists of layers of artificial neurons. Each neuron receives inputs, multiplies them by weights, sums the results, and applies a nonlinear function. The outputs become inputs to the next layer. The final layer produces the prediction. Initially, all weights are random, so predictions are nonsense. But you can measure how wrong the predictions are and adjust weights to reduce error. Backpropagation, an algorithm from the 1980s, efficiently computes how each weight contributes to error and updates weights accordingly. Repeat this millions of times with millions of examples, and the network learns. Deep neural networks have many layers, hence deep learning. Each layer learns to detect patterns at different levels of abstraction. In image recognition, early layers detect edges and textures. Middle layers combine these into parts: eyes, ears, wheels. Late layers recognize whole objects: cats, cars, faces. These representations aren't programmed. They emerge from training. Show the network millions of labeled images. Adjust weights to minimize classification error, and it discovers hierarchical features on its own. This is remarkable. The programmer doesn't specify what features matter. The network learns them from data. Deep learning revolutionized AI around 2012, when neural networks dramatically outperformed traditional methods on image recognition. AlexNet, a deep convolutional neural network, won the ImageNet competition with unprecedented accuracy. Since then, deep learning has dominated. Speech recognition, machine translation, game playing, medical diagnosis, drug discovery. AlphaGo, developed by DeepMind, defeated the world Go champion in 2016. Go is vastly more complex than chess, more possible positions than atoms in the universe. Brute force search fails. AlphaGo combined deep neural networks with reinforcement learning, improving through self-play. It developed strategies human experts had never seen, demonstrating creativity in a domain where humans had centuries of accumulated knowledge. Yet AlphaGo doesn't understand Go the way humans do. It evaluates positions through learned pattern recognition, not through conceptual understanding of territory, influence, or strategy. It plays brilliantly without comprehending what it's doing. Large language models, like GPT, generate coherent text by predicting what word comes next. Trained on billions of words from the Internet, they learn statistical patterns in language. Given a prompt, they generate continuations that sound plausible because they've seen similar patterns in training data. These models can write essays, answer questions, translate languages, generate code. The output is often impressive, sometimes indistinguishable from human writing. But the model doesn't understand meaning. It manipulates symbols based on statistical correlations without grasping what the symbols represent. This is the distinction between pattern recognition and understanding. Humans recognize patterns, but also build mental models, concepts, causal relationships. We understand that the cat sat on the mat describes a physical situation with spatial relationships and agency. A language model predicts that mat often follows on the in this context, but doesn't construct a mental image of the scene. Can machines ever achieve genuine understanding? Some argue it's impossible. Understanding requires consciousness, subjective experience, qualia that computation can't produce. Others argue understanding is just sophisticated information processing, and sufficiently advanced systems will eventually achieve it. The Chinese room thought experiment, proposed by philosopher John Searle, illustrates the puzzle. Imagine someone who doesn't speak Chinese locked in a room with a rule book. Chinese messages are passed in. Following the rulebook, the person manipulates symbols and passes out responses. To outside observers, the room appears to understand Chinese, but the person inside doesn't understand. They're just following rules. Searle argues this is like computers running AI programs. They manipulate symbols according to rules without understanding what the symbols mean. The system produces correct outputs without genuine comprehension. Critics respond that while the person doesn't understand, perhaps the system as a whole, person plus rulebook plus process, does understand. Understanding might be a property of the system, not any single component. Similarly, individual neurons don't understand, but brains do. This debate remains unresolved. What's clear is that current AI lacks several capacities humans have. Humans learn from few examples, see one zebra, recognize all zebras. AI requires thousands of examples. Humans transfer knowledge across domains. AI trained on cats doesn't automatically recognize dogs. Humans understand causality. AI learns correlations without grasping cause and effect. Common sense is particularly challenging. Humans know that solid objects don't pass through each other, that dropped objects fall, that people have beliefs and desires. This knowledge is so basic we rarely articulate it. But AI systems lack this background understanding, leading to failures on tasks any child handles easily. Adversarial examples expose AI limitations. Slightly modify an image, change a few pixels imperceptibly, and image classifiers misclassify it wildly. A panda becomes a gibbon with 99% confidence despite looking identical to humans. The classifier learned surface patterns without robust understanding. AI systems also inherit biases from training data. If training data reflects societal inequalities, the model learns and perpetuates them. Hiring algorithms trained on historical data favor candidates resembling past hires. Disadvantaging underrepresented groups. Facial recognition performs worse on darker skin tones because training data overrepresented lighter skin. These aren't just technical problems, but ethical ones. As AI systems make consequential decisions, approving loans, recommending sentences, diagnosing diseases, bias and lack of understanding have real-world impacts. Explainability is another challenge. Deep neural networks are black boxes. Millions of parameters, complex, nonlinear interactions. Why did the network make this prediction? Often, even the designers don't know. The network learned correlations in data, but which features mattered? This opacity is problematic when decisions require justification. Despite limitations, AI capabilities expand rapidly. GPT-4 and similar models generate remarkably coherent text, answer complex questions, and write functional code. DALL-E and Midjourney create realistic images from text descriptions. AlphaFold predicts protein structures with unprecedented accuracy, advancing biological research. These aren't general intelligence. They're narrow systems, each excellent at specific tasks. But they demonstrate that many tasks thought to require human-level intelligence can be automated. Not through understanding, but through pattern recognition at scale. Will we ever build artificial general intelligence, AGI, matching human cognitive abilities across all domains? Opinions vary wildly. Some researchers predict AGI within decades. Others believe it's impossible or centuries away. The uncertainty stems from not understanding intelligence deeply enough to know how to build it, or whether current approaches can scale to general intelligence. There's also the question of whether we should build AGI. Superintelligent systems might be uncontrollable, pursuing goals misaligned with human values. This isn't science fiction, but a serious concern among researchers. An optimization process powerful enough to improve itself recursively could rapidly become incomprehensibly capable, potentially threatening humanity if not carefully designed. Alternatively, AI might remain narrow, excellent at specific tasks, but never achieving general intelligence. We might have systems that drive cars, diagnose diseases, generate art, translate languages, each specialized and superhuman in its domain, but none possessing the flexible, general reasoning humans have. Current AI is impressive pattern recognition, statistical correlation on massive data, optimization of complex functions. It's not understanding, consciousness, or thought in the human sense. But it's also not mere calculation. It's something in between, a new kind of intelligence foreign to biological minds. Machines have learned to recognize faces, understand speech, play games, generate text and images. They do things that look intelligent without, perhaps, being truly intelligent. Whether this distinction matters depends on your goals. For practical purposes, capability matters more than consciousness. But philosophically, the question remains open. Can machines think? Do neural networks understand? Is consciousness necessary for intelligence, or is sophisticated information processing sufficient? We've built thinking machines in the sense that they perform cognitive tasks. Whether they think in the sense of subjective experience, we don't know. What's certain is that we've crossed a threshold. Computers are no longer just tools that follow instructions. They learn, adapt, and solve problems we don't know how to solve explicitly. They're becoming partners in discovery, creation, and decision-making. We taught sand to think by organizing it into transistors. We taught transistors to learn by organizing them into neural networks. We taught networks to recognize patterns by showing them data. Each step built on the previous, abstracting from switches to logic to algorithms to learning. And now we stand at a new frontier, where machines approach capabilities once thought uniquely human. Where that leads, whether to genuine artificial minds or just increasingly capable tools, remains to be seen. Silicon Dreams. We began with a mystery. How do you make rocks think? The answer, as we've discovered, is layers. Layers of abstraction, each building on the one below, each hiding complexity while enabling new possibilities. At the bottom, transistors, microscopic switches carved into silicon. Above them, logic gates combining switches into operations. Above those, processors executing instructions. Above those, programming languages expressing algorithms. Above those, applications solving problems. And now, at the top, machines that learn, recognize patterns, and perform tasks we once thought required human intelligence. None of this was inevitable. Every layer represents insights, breakthroughs, sometimes accidents that someone turned into innovations. Turing proving that universal computation was possible. The transistor replacing fragile vacuum tubes. The stored program architecture separating software from hardware. High-level languages making programming accessible. The Internet connecting isolated machines into a global network. Neural networks learning from data rather than following explicit rules. each advance built on previous ones, creating capabilities unimaginable to earlier generations. The engineers building ENIAC couldn't have conceived of smartphones. The researchers creating ARPANET couldn't have predicted social media. The scientists developing early neural networks couldn't have imagined GPT or DALL-E. Yet here we are, surrounded by computers. They're in your pocket, on your wrist, in your car, your appliances, embedded in infrastructure managing power grids, traffic systems, financial markets. Computing has become invisible through ubiquity. We interact with computers constantly without thinking of them as computers. This transformation happened in living memory. In 1950, there were perhaps a few hundred computers worldwide, each filling rooms requiring specialized operators, serving research institutions and militaries. By 2000, personal computers were common in homes and offices. By 2025, billions of people carry supercomputers in their pockets, connected to a global network, accessing more information than existed in the entire Library of Alexandria. The pace of change follows Moore's law, transistor count doubling every 2 years, but also broader trends. Storage capacity increases. Network bandwidth expands. Algorithms improve. Each advancement enables new applications that become infrastructure for the next generation. Consider what's now routine that seemed impossible decades ago. Real-time video calls across continents. Instant access to humanity's accumulated knowledge. Navigation systems guiding you through unfamiliar cities. Machines recognizing faces, understanding speech, translating languages. Computers defeating world champions at chess, Go, and increasingly complex games. Artificial neural networks generating realistic images from text descriptions. Writing coherent essays. Composing music. These capabilities raise profound questions. What does it mean to think if machines can perform intellectual tasks? What is creativity if algorithms generate art? What is intelligence if systems learn without understanding? The answers remain uncertain. Current AI is pattern recognition at scale, statistical correlation in high-dimensional spaces, optimization of complex functions. It's impressive, useful, sometimes unsettling. But it's not consciousness. It's not understanding in the human sense. Neural networks manipulate symbols without grasping what symbols mean. Language models generate coherent text without comprehending content. Image classifiers recognize cats without knowing what cats are. This might change. Perhaps scaling up current approaches will eventually produce genuine understanding. Perhaps consciousness emerges from sufficient complexity in information processing. Perhaps artificial general intelligence is achievable through refinements of existing techniques. Or perhaps we're missing something fundamental. Perhaps understanding requires embodiment, interaction with the physical world in ways current systems lack. Perhaps consciousness involves quantum effects. Biological processes that silicon can't replicate. Perhaps there's a qualitative difference between human thought and machine computation that no amount of optimization can bridge. We don't know. What we do know is that machines can do things that look intelligent without necessarily being intelligent in the way humans are. This is both reassuring and concerning. Reassuring because it means intelligence might be less mysterious than we thought, reducible to information processing. Concerning because it means we can build systems with enormous capability that lack judgment, common sense, and understanding. The future of computing is uncertain, but trending toward several frontiers. Quantum computing exploits quantum superposition and entanglement to perform certain calculations exponentially faster than classical computers. Quantum computers won't replace conventional computers. They're specialized for specific problems. But they'll enable breakthroughs in cryptography, drug discovery, materials science, optimization. Building reliable quantum computers remains challenging, but progress continues. Neuromorphic computing mimics brain architecture more directly than conventional processors. Instead of separating memory and processing, neuromorphic chips integrate them, potentially overcoming the von Neumann bottleneck. Instead of clocked sequential operations, they use asynchronous event-driven processing. This could enable more efficient AI, particularly for pattern recognition tasks. Biological computing uses DNA and other biological molecules to store information and perform computation. DNA storage is incredibly dense. All the data humanity has ever created could fit in a small room if encoded in DNA. Biological circuits could interface with living cells, enabling medical diagnostics and treatments. Edge computing moves processing away from centralized data centers to devices themselves. Your phone, your car, your security camera increasingly run AI locally rather than sending data to the cloud. This reduces latency, improves privacy, and works when networks are unavailable, but it requires more capable local processors and efficient algorithms. These technologies share a theme, moving beyond the constraints of conventional computing. Quantum computation escapes classical limitations. Neuromorphic computing escapes the von Neumann bottleneck. Biological computing escapes silicon entirely. Edge computing escapes centralization, but they also share challenges. All require fundamental research, engineering breakthroughs, manufacturing advances. None will replace conventional computing soon. They'll supplement it, handling specific tasks where they excel. Meanwhile, conventional computing continues improving. Transistors shrink toward atomic scales. Chip designs become more sophisticated, with specialized accelerators for AI, graphics, signal processing. Three-dimensional chip stacking increases density. Novel materials like graphene and carbon nanotubes promise speed and efficiency improvements. Software advances too. Algorithms become more efficient. Languages evolve. Development tools improve. Open source collaboration accelerates innovation. Machine learning discovers optimizations humans wouldn't find. AI increasingly writes code, designs chips, even invents algorithms. This raises questions about human roles. If machines can code, what do programmers do? If AI can design, what do engineers do? If algorithms can discover, what do scientists do? The answer isn't that humans become obsolete, but that our work changes. Programmers shift from writing every line to designing systems, choosing architectures, solving novel problems. Engineers move from routine calculations to creative design. Scientists ask questions machines can't formulate and interpret results. Machines can't contextualize. Human cognition and machine computation are complementary. Machines excel at scale, speed, pattern recognition in high-dimensional data. Humans excel at abstraction, creativity, common sense, understanding context, asking meaningful questions. The most powerful approach combines both. But this assumes careful design of human-computer interaction. If machines are opaque black boxes, humans can't effectively guide them. If AI makes decisions without explanation, humans can't evaluate correctness. If systems inherit biases from data, automation perpetuates inequality. Responsible AI development requires transparency, explainability, fairness, accountability. These aren't just technical challenges, but ethical and social ones. How should we design systems that affect people's lives? Who's responsible when algorithms make mistakes? How do we ensure benefits are distributed broadly rather than concentrating power? These questions don't have easy answers. Technology creates possibilities. Society determines how to use them. Computing can enable surveillance or privacy, concentration or distribution of power, equality or inequality. The technology itself is neutral. The choices about deployment, regulation, and access determine outcomes. The democratization of computing has been remarkable. Smartphones cost hundreds of dollars and provide capabilities that would have cost millions decades ago. Open-source software makes professional tools freely available. Online education teaches programming to anyone with internet access. The barriers to creating software, starting companies, reaching global audiences have never been lower. But digital divides persist. Access to technology, education, and opportunity remain unevenly distributed. Some populations lack reliable internet, capable devices, or educational resources to participate fully in the digital economy. Closing these gaps requires policy choices. Infrastructure investment, educational programs, not just technological advancement. Looking forward, computing will continue embedding itself deeper into civilization. Already, it mediates communication, commerce, entertainment, education, healthcare. As AI capabilities expand, more decisions will involve algorithmic components. As automation advances, more labor will shift from human to machine. This transition could be utopian, freeing humans from drudgery, enabling creativity and leisure, or dystopian, concentrating wealth, eliminating jobs, creating permanent unemployment. Which future we get depends on choices made now about education, social safety nets, wealth distribution, worker retraining. The technical trajectory is somewhat predictable. Computers will continue getting faster, smaller, more efficient. AI will continue improving at pattern recognition and specific tasks. Networks will expand. Latency will decrease. Bandwidth will increase. These trends follow from physics, economics, and accumulated knowledge. The social trajectory is less certain. How will we adapt to AI-driven automation? How will we regulate increasingly powerful technologies? How will we maintain privacy in a connected world? How will we ensure AI systems align with human values? These questions have no technical answers, only social and political ones. Standing at this moment in history, we can reflect on what we've built. In less than a century, we went from room-sized calculators to pocket supercomputers, from isolated machines to a global network, from programmed automation to learning systems. We've taught sand to think, not through magic, but through layers of clever abstraction built on fundamental physics. Every level of this stack is remarkable. Transistors switching billions of times per second. Processors executing billions of instructions per second. Networks transmitting billions of bits per second. Software coordinating billions of operations to produce the experience of using a computer. something that feels seamless and simple despite the astonishing complexity underneath. And yet, for all we've achieved, we're still at the beginning. Computing is perhaps a century old, depending on where you market start. Transistors are 75 years old. Personal computers are 50 years old. The web is 35 years old. Deep learning's renaissance is 12 years old. These technologies are young, still evolving rapidly. What computing looks like in another century, we can barely imagine. Will we have achieved artificial general intelligence? Will quantum computers solve problems currently intractable? Will biological computing integrate with neural tissue, blurring the line between human and machine? Will we upload minds, simulate consciousness, transcend biological limitations? These questions veer into speculation, science fiction, philosophy. What's certain is that computing will continue evolving, driven by human curiosity, commercial incentives, scientific inquiry, and the accumulated momentum of decades of progress. We built thinking machines from rocks. We created intelligence, or something indistinguishable from it for practical purposes, from switches. We connected billions of devices into a single integrated network. We taught machines to learn from data, generating capabilities we didn't explicitly program. Each step seemed impossible until someone made it real. Each innovation built on previous foundations, enabling new possibilities. Each generation of technology created tools for the next generation to build upon. The story of computing is humanity's story, of curiosity, ingenuity, creativity, and perseverance, of taking the raw materials of nature, understanding their properties, organizing them into structures that transcend their components, of building layers of abstraction until complexity becomes manageable, until rocks think, until the universe examines itself through mechanisms it created. This should be impossible. For most of history, it was. Now it's everywhere, invisible through ubiquity. Infrastructure. We barely notice except when it fails. We've built thinking machines. Where they lead us remains to be written.